Is this loud enough on Zoom? Yeah, so, well, neuromorphic computing, as it's called today, or neuromorphic engineering, as it was called in the early days, has come a long way. And so now, the great thing is now when you go somewhere to conference and talk about this, what are you doing? You think, should I say neuromorphic engineering? Because they won't know what it is. Today, now you can just easily say it because everyone knows about it. Even in industry, you go to, right, they all know what it is. Except the definition of the term has somewhat transformed over the years. And so let's go back to the future here and go back to the biophysical foundations. This will be more or less a tutorial of where the field started, and with perspective also where we're going from there, right? So let me motivate us. So here's a transformative moment that we all experience. And so for many years, right, you had AI on one side and neural nets on the other side. And those two were not talking to each other. In fact, they were fighting each other. There was a symbolic AI, all this very clean, crisp digital stuff, right? This very precise. And then there was the neural networks, which was considered by the AI people to be the noisy, the imprecise, the messy stuff, right? And here's a moment. So for many years, AI had all these holy grails of in fact, there was this meeting at the beginning of AI, right? Where the whole thing was going to be a summer workshop. And so after the summer, all of AI would have been solved, right? It was clear it didn't happen. And
yeah,
so,
all of computer vision, according to, who was the guy, Minsky?
yeah,
Minsky said, oh, we'll just do computer vision, summer student can solve it.
summer enrichment kind of thing. Yes. So these were very hard problems, right? And then afterwards, it dawned on the field that AI will take a long, long, long time, and so you would never solve a hard problem like computer code. This was a really hard problem, and nobody could really solve it with traditional, right, AI. And then there came along this moment that Google DeepMind. Now, DeepMind was founded by neuroscientists. So the neuroscientists, the people that were doing computational neuroscience or fMRI kind of processing or analysis of brain data. And sure enough, they had some knowledge of how the brain is organized. Layered architectures, basal ganglia doing this reward conditioning, right? So there came deep reinforcement learning as a concept that solved this problem of computer code and defeated then the world champion in the game. Now, to put things in perspective, so yes, this was Google, right, and defeating the human here, right, and with all of what they had, right, with Google with deep pockets, doing deep learning, and so literally, if you look here at the comparison, right, so so you have about 100 watts, liberally estimating the power that the human will expend at the game beyond the brain, also the arms or whatever, right, the whole body was in the game. Versus the machine. And the machine is 100 kilowatts, so that's 1,000 times more power. Those are those well, not the GPUs, those were TPUs, tensor flow processing units that Google developed. They were the workhorse for doing all the computation. So clearly there's a mismatch here in the power that is expended for doing this. And it gets even worse. So sure, we have had amazing advances in the accuracy, the precision of AI systems. All of these AI systems are now neural network infused, right? But so in terms of inspiration from the brain is all great. But so right, so we had this amazing kind of advances in the almost logarithmic advances in the performance of the systems over the years. But those advances have come at a humongous cost of the amount of computation that is involved. On the horizontal axis here, these are computations, it's billions of operations. Right? Sure, you had about, say, 1 order of magnitude improvement in error rate, but this came at 8 orders of magnitude in computational operations. Right? And that, of course, also translates to power, right? That 8 orders of magnitude, the greater power that it takes for for training those systems, right?
I have to be the peanut gallery here and say, so what? You know, these are big corporations that are training this, and they use it after that for millions and millions of people. So what if it costs them a million?
So look at this. So
It's nothing.
yeah, so look, basically now to train one of those systems, it takes as much power as the power.
Yeah, but so what? That's nothing in the world, right? These are billions of people that are using this system. It's just nothing.
So global warming, so now a
Okay.
significant fraction, so now it's becoming like what, 5-10%? So if you keep going this way, right? So
The numbers are bullshit. It's not so high.
well,
You have to give us the execution.
okay,
cost,
that's obviously right. It's not, it won't be this high because fortunately in this room we have neuromorphs and we know how to fix the
And
problem.
all of industry is improving power efficiency all the time too.
Exactly.
It's
Yeah,
bullshit. Yeah.
Yes, well, yes,
Okay.
so let's look at where things, so we have this axis here of energy efficiency, depending whether you like the cup half full or half empty, right? So you have one axis is energy for operation, and of course I will minimize that. The other axis is then operations per second per watt, same thing if you do one over, right? Right, and so either way, right? So this one is the one over the other, right? And so let's first look at fundamental limits. The Landauer limit tells us that, well, if you really want to distinguish two states in a system, binary, right? So the 0 and the 1, you need to at least have an energy barrier somewhere that can hold those states, separate those states from each other, right? By at least a thermal energy, because if not, then just noise will just, your SNR, right? Your SNR will be 1 if you just have the barrier, right? So if you want to at least have an SNR of 1, 0 dB, then at least you have this energy barrier that is around KT, right? KT is the thermal energy. There's also 11.2 there, but that's just minor details. So that's basically the limit here, right? So really low, 10 to the minus, it's basically almost like 10 to the minus 20 or so joules per operation. Now let's see what computers yesterday have been doing, and those are the CPUs and then right. So and that's about, so disregarding the actual cost for the compute itself. Most of the compute is not dominated by the compute itself, but by by getting to the memory, because in the neural network, most of the operations you can use your weights once, mostly, right? Because especially large language models, you can use it once and that's it. So the compute energy is dominated by the energy of getting the bits from the memory. And so then here, if you have DDR3 memory, right, so it's about 70 picojoule per bit, so that's about 0.5 nanojoule per Mac, right, if you have 8 bits of accuracy. So that's orders of magnitude away, right? And let's compare this with the brain. So the human brain, so let's have a rough estimate here. Very simple, right? So we have about 10 to the 12 neurons, about 10 to the 15 synapses. And so neurons fire about an average between 1 and 10 hertz, let's say 10 hertz, right? So 10 times per second. So synapses get activated, right? 10 times per second. So that basically means you have 10 to 50 synapses at 10 hertz, that's 10 to the 16 synaptic operations per second, right? So that's the throughput. And now what is the power? Roughly speaking, around 10 to 15 watts of metabolic power. It's not that much power. In fact, the argument that is made is that we have hair in our skull, or most, right, in order to keep our brain, I guess, warm enough. So the heat dissipated by the brain is not enough to keep us warm, especially during the winters. Right? So yes, it's 10 watt power. So and the ratio of those two is then 10 to the 15 ops per second per watt, or 10 to the minus 15 femtojoule per synaptic operation. Right? So that's somewhere in the middle here, closer to the Landauer limit. So clearly there's much work to be done here. And then, so how have things fared over, so now the latest advances you've had with FPGAs, GPUs, all this NVIDIA revolution that we've had, right? We only got a factor 10 or so improvement. Sure, the compute has gotten much more efficient, and NVIDIA will tell us, right? Sure, oh yes, we have sub femtojoules per multiply cumulative, but that doesn't count for the fact that you need to get the data in. You need to get your data, both your weights and your data, you need to get it in. And that's, so again, you have now slight improvements now. So with HBM, high bandwidth memories, picojoules per bit, right? So it's still now in the upper picojoules per Mac efficiency. So still far. So now clearly now, so if the problem is getting the data, right? Getting the memory closer to the compute, then the logical thing to do is you choose either you bring the memory into the compute, or even better, you bring the compute in the memory, right? So then rather than having
Sorry,
this,
I have to be another peanut gallery. I have to say that these numbers are also misleading because they don't regard memory reuse.
yes, and now we're talking about convolutional networks, right?
Yeah, or anything that shares weights, right? And I think it's misleading, a little bit misleading.
Yeah, no, yes, absolutely. Yes, and NVIDIA has been so successful because they've been able to, and the reason why we all heard about conv-nets for so many years is because GPUs,
And all the accelerators that people built,
they
not
were
just,
all optimized for these convolutional operations, right? And sure, yes, weight reuse basically means, you can recycle the same weights because you use
1,000
them.
times, you know?
Yeah, we have this template, the convolutional template that plays over.
No, it's not an upper limit 1,000 times, you know, you just have 100 feature maps in your kernel is like 3 by 3, that's already 1,000 times.
You've got dense layers and LLMs, so I think you.
Yeah, but.
That's
Not
exactly,
dense
yes,
layers,
yes.
Okay.
So confidence, absolutely. But now then came along the large language models, right, transformers, and now even the latest advances in even for vision, you use transformers as opposed to using context. So there's a, and that revolution has been enabled us. The fact that NVIDIA has realized that the future is no longer graphical or graphical processing accelerators for gaming, but the future is in learning and machine learning. And so that the latest GPU processors are actually great sparse, matrix algebra processors, just like the same way as we're doing here. So in that regard, NVIDIA is now doing neuromorphic too. In fact, one of the founders of NVIDIA is Dave Kirk, right?
Yeah, but he stopped doing the architecture years ago.
I know, but he was at Caltech also at the time that Harvard started the field, right? And he did one of the first learning chips, on silicon learning chips, and he wanted to get the vision of starting a company that would accelerate vision or accelerate basically the graphics, and it was going to be all analog. And the first chips that did were analog, but then eventually all digital. Okay, so that's the brain, and the computer memory. So you do a bit better than that. I'll say a bit more about how we can actually get closer to even brain efficiency with memoristive computer memory devices. So again, you bring the compute inside the memory because you want to do parallel processing, right? Because normally you have this arrays of memory cells, right, that you access mostly sequentially in today's systems. But why not take advantage of this massive storage that we have, slow, massive storage, that's what we have, right? And then do this distributed computing inside of its pixel or inside of each cell. And so that's the premise. In fact, that is one of the magic of neuromorphic computing in the way we all started. What's it called today, computing memory. We have been doing this over the last 30 years. And I'll say that actually you can even go beyond efficiency of brain computing if you use some tricks of adiabatic energy recovery in charging and computing. It's more. Okay, that's an overview. So let's dive into it. So the field of neuromorphic engineering was founded by Cauwenberghs as a realization, right, that in order to get really great modeling of how the brain works, it is more than just looking at the algorithms, but you also have to look at how the brain is organized in how it computes and look at the biophysical principles of how you can get this efficient and resilient computation happening in brains, and then literally transform that, morph that, right, into electronic silicon-based systems, owing to the fact that the physical principles, even though solid state physics is very different from this ion, this type of the biophysics, there are some commonalities between the physical domains that can be exploited, and that's what drives them neuromorphic computing. So that's a setting, and of course, learning and adaptation is the key for then getting that really great resilience and adaptive power of that computing. So that's the premise, and this started 30 years ago, 35 years ago. But in a way, even before that, so we all have heard about John von Neumann, who's a great mathematician. And so today, the field of neuromorphic computing sometimes also refers to this. So neuromorphic computing or quantum computing, right? They're all called non-polynomial computing. That is the greatest insult to John Harmon, because he actually was the one who contrasted the brain and the computer, right, in his last work just before he died.
But how many people read this? How many people read this book here? Okay, it's a really nice book. It's easily readable, you know, just in bed while you're, you know, driving somewhere or something. And basically, I mean, I have to say more, I think this book is really cool because it basically outlined at the time of the end of World War II, the different kinds of computers that were being built. One were like special purpose computers, analog or digital. Another were general purpose computers. You know, and these two main kinds of computers still exist, you know, FPGAs and logic circuits are special purpose, and CPUs are general purpose. So those ideas still stuck around, and he wrote them down very clearly, and then he contrasted them with brain computing as it was known at the time. I think it's a really lovely piece of work. Like it's a story that you can read.
This is almost the
really cool.
required reading for
Yeah, and I
everyone.
think you can probably get it for free now, but
Oh yeah, you can get it online.
you get it online, yeah.
There's a nice version of that also was written.
He
with the
didn't,
foreword
he didn't
of the-
realize those computers, but he was very good at writing down how they were built, you know, at making it, explaining how they were built at that time.
Yeah.
And not getting too much into the vacuum tubes and things like that, basically the principles of designing them.
Yeah. So very simply, right? So you have a stark contrast between sequential processing, right? That you have fast sequential processing, right? Of the compute, and then you have this memory that is slow and
Or dedicated finite state machines
Yes.
and programmable
So
machines.
this is a sequential finite state machine that does the processing, and then you have this memory that kind of interfaces to it. And the brain is the totally opposite, right? So there you have massive parallelism, right? Every element computes at the same time, and you get this parallelism is one thing. The other thing, you get this amazing resilience because you get this fault tolerance owing to the fact that you have this redundancy in the computation, right? These large numbers, right? Hyperdimensional computing is also what is called today. And so, yes, it's amazing that by having these collections of noisy, sluggish elements, you can still do very precise, fast computation owing to the fact that you have this massive parallelism.
Well, that was his hope. No, that was his explanation of how the brain did it, right? But it wasn't,
It wasn't
there was no
done.
realization, right?
This was the observation. So
That was
the
the
brain,
observation,
that's what happens in the brain. And so the challenge that we put forward is, why don't you actually, this would be another way of doing computing, especially related to cognitive computation. Anything cognitive would make more sense doing it that way as opposed to the sequential processing that is more important if you know the cognitive.
So I think it's true in the hardware, there's nothing about, but in the software, there's a lot of sequential processing. But here when you talk about computing.
Yes. Well, you know, this will be a great. So there's plenty of. We're not negating all the advances that we made in AI or the symbolic, right? There's also a lot of symbolic reasoning that we have to model too, the higher level things, right? And so a convergence that we're seeing now, for instance, large language model, there's a lot of great stuff that is, I mean, Bayesian inference is extremely important, and it's good to bring those things together. But at least the computation substrate, we can think of more efficient substrates for doing this kind of massively parallel computation, coupled, of course, with other things like bottom up, top down kind of things, right? Where definitely there's also, we think, right, after we do reason, after all. But the underlying substrates, the bottom up stuff should still be with this massively parallel processing. That's the premise here. And that came along. So here is Richard Feynman, who told us many things like there's lots of room at the bottom, and that in many ways you can think of started a revolution in nanoscience, right? By shrinking things down, being able to get really amazing computational high density systems, right? At nanoscale. And so he was also an advocate for quantum computing, going down to the nanoscale, right? For doing this fundamental limits of computing at the quantum level. And Carver Mead, he also Caltech, right? In fact, you would call him the founding father. I'll get to that point in a minute. Of neuromorphic engineering. He also saw this great potential. So he was a great friend of Gordon Moore, founder of Intel. In fact, Carver Mead, so he started this field he realized the scaling properties of silicon that would allow them really construct systematic systems, right, of digital computing, and then he saw this wonderful scaling laws. Everything got better by just scaling it, right? As you shrink the technology, make the feature sizes smaller, everything gets better. The speed gets better because now you get shorter transit times for electrons. The power gets better because now as you shrink, capacitance go down, right? And of course, density gets better. You can do more, right? You can lower cost, right? You can do more compute per area. And so, Gordon gave this talk once where he predicted, right? He's going, but the term Gordon, is a Moore's law, has been actually coined by Carver Mead. And so, so that's all digital design. But there comes along analysis by synthesis, right? So that so Richard Feynman also, one of the last things he said before he died, actually, right? What I cannot create, I do not understand. Right? Pointing out, if you really want to understand something, you actually need to put it together yourself, synthesize it, right? Demonstrate it. So if you want to understand how the brain works, you need to put together a brain. That's right. And Carver took this to heart. And in fact, so those two, along with also John Hopfield, were teaching this course at Caltech in the late in the 80s. Right, about different ways of looking at computation related to how the brain works, right? Or the physics of computation, the fundamental physics of computation. Richard Feynman was all about quantum computing. Then we had John Hopfield was all about this physical principles, right? This spin glass systems, right? This Boltzmann energetics of neural networks, right? And Carver was pondering the idea of how to actually model how the brain works and try to go back on the directions of John von Neumann, right? And in fact, so there was this very bright biology student who was taking that course, and she said she didn't understand anything was happening in this course. It was all above her head. But one thing that she really realized is that, hey, yes, computation has been done today at that time, 30 some years ago. It's not the way it should be done. And so there must be better ways of doing it, taking direct inspiration from biology, neurobiology, and then build better computation systems inspired by biology, right? And so, in fact, she did amazing stuff, right? So the first silicon neurons, the first silicon retinas in Carver labs, right? The time and so this was great. So Misha was there, Toby, Chichi, in fact, many of us were also there at the same time. Raf, yes.
Yeah, so along that timeline, right? The first neuromorphic circuit to be implemented on the bench was Paul Mueller's in 19.
Oh yeah, yes. Oh, absolutely, yes. Sorry, yes, absolutely, yes. Plenty, yes, there's plenty of great. Yeah, so it's not just that. But one thing though that is, so Carver gave a beautiful perspective. He's now 90 years old. In fact, his birthday is just a few months ago. Still active, really great. In fact, we had this conference, the NIC conference. I know we have a nicer venue here, but the NIC stands for Neuro-Inspired Computational Elements. This is a conference that's been ongoing now for several years. It was in San Diego last just a month or so ago. And
if you could turn on your microphone right now, it's the sound quality from that webcam not very good, right?
okay.
Should just be right there.
We'll see how that goes.
Okay, can you hear me? Okay, good.
Thumbs up there on that. I'll check with them. We'll see how that goes.
Great. Okay, so yes, we had so Carver actually showed up, he was there, and he gave a perspective of the field. In fact, it's recorded, so I highly recommend, just click this link, the slides we posted on the or you can just Google it, right? NIC 2024, right? So all the lectures are recorded and posted. In fact, any year the NIC workshop, everything has been recorded in the past, and you can click the links, right? But so yes, Carver gave a beautiful perspective to be introduced,
I said it wasn't my idea; it was Misha's idea.
Exactly.
Someone said, let's do it
Yes.
right now.
Yes.
You know, after she took his course, right? I'm not quite convinced about that. He might be like giving the credit.
I actually know, I believe about,
It's possible.
of course, Carver is very nice, but so, no, he definitely had,
knew about Fukushima's work and Carver
Yeah.
knew about Fukushima's work, right?
Yeah. But she was his first student
I know.
and challenged Carver to really do it. And of course, Carver made humongous
He liked
contribution
that
to the field.
because he was sick of this logic synthesis stuff, you know, all this silicon compiler stuff. It all became so complicated.
Yeah.
You know, so industrial.
So Carver is amazing. So he went, he did the digital VLSI revolution.
Yeah.
He started that. Then he did neuromorphic computing. Then afterwards he
Just
got
before he
targeted.
did this stuff, he did systolic. You guys ever heard of systolic arrays? Systolic logic arrays? Yeah, these are basically dedicated logic circuits that where the data flows through them. As the data flows through, as I understand, the computation is done. So it's a lot like a CNN modern accelerator, but they were much more restricted in those days. And just before the neuromorphic stuff, he did a bunch of stuff with systolic arrays to do digital signal processing, like sound synthesis, to make like musical instruments with these digital systolic arrays. And this is very early in the days of digital
Yeah.
logic design, where you couldn't just write Verilog and it was few big logic circuits. So it was really, you know, it's kind of revolutionary at the time to build these dedicated logic circuits to do signal processing. But that was,
Yeah.
as the parallel computation of those logic circuits that probably inspired also the neuromorphic stuff, which is mixed,
Yes.
you know, analog circuits and something.
Making even another connection to the workshop here, he also started this auditory modeling and
Yeah, that's right. That was a big line, I think. they got it.
with yes, and John Lazaro and others, yeah. And then now he's doing quantum electrodynamics. He has also a beautiful book in that as well. And okay, so that's where the field really, I guess, took off. So as a synergy between engineering and neuroscience, science is always about analysis, right? You try to understand something from fundamental principles, and then so that's a typical top-down approach. Right? You go down to the lowest level that you can, where you can fully characterize your system, so this is really a top-down kind of approach to doing science, right? Engineering is the opposite; it's the complementary approach to synthesis. You put things back together by abstracting at each level of representation the fundamental principles, and then building up systems, right? This basically from the ground up, is the bottom-up approach, and that allows then combining this analysis synthesis with neuromorphic computing allows you to do, in principle, whole brain dynamics. You can do the modeling with. That's what we're going now with cognitive neuromorphic engineering or neuromorphic cognition engineering. We can really start synthesizing function and structure of neural systems at full scale, right? With an entire stack here of different levels of representation, right? From whole brain at the top here down to the single elements at the bottom. And it just so happens that at each level, there are those physical isomorphisms between the biphysics, ions, right, and the wet stuff, right? And then the solid state physics, or the physics, right, of what happens in the computational systems in silicon. And so, for instance, here at the higher scales, you have the Boltzmann machines, right, or the Boltzmann dynamics. And so John Hopfield tells us about the Hopfield networks, these glass systems. And sure enough, this now is becoming important. The latest systems, you have Boltzmann machines, actually very powerful initial neural systems for doing generative modeling. And now there's all these advances with larger Bayesian systems, variational autoencoders, now all these transformers, right? And stable diffusion, all these things that are generative, that they can be modeled after those. There's some energy distributions that they can be modeled at those levels. But at the bottom level of this, there is the direct biophysical analogy, right, between transport of, say, electrons in an NMOS transistor or holes in a PMOS transistor, either way, right? And you have this energy barrier that's implied by the gate, right? So, and the volts in the gate will then lowering either lower or higher because the barrier. And normally, when you use in the old days, when you learn about an MOS metal oxide transistor, you think about this above threshold equations, right, that govern how transport is above threshold basically is drift, right? So where the barrier is basically gone, and then now you have mostly you have a drift dominated mechanism of transport. But you have a beautiful domain of operation, which is typically called cutoff or leakage, right? In this above threshold style of circuit design. And that's a sub-threshold domains, below the thresholds. Below threshold, normally above threshold, you would think the model, say there's no current, but there's absolutely current, owing to the fact, and Carver beautifully illustrated that in his book, right? There is current because you have this vapor, if you want. You have this Boltzmann tail. So if you don't think of flow of your carriers as a liquid, but you think of it as something else as a vapor to it, an energy distribution, right? Sure, as you increase your energy barrier, there's still some vapor that can make it over the barrier. And so the lower the barrier, the more current you get in exponential fashion. The same way as you look at the distribution, say, of vapor, right? Or you get exponential distribution due to the balance between drift and diffusion, right? The Boltzmann distribution is the balance between drift and diffusion, right? And so in the diffusion limit, you get this Boltzmann tail that tells you the higher the barrier, the less exponential, less current that you have. But it's beautiful because now we can get currents that are nanoamps down to femtoamps of current. You can get 6 orders of magnitude or more of dynamic range in very low current, and that's exactly where we like to operate in massively parallel, very slow computing, right? Where we now do things at a kilohertz or at most a megahertz scale, not gigahertz, and all operate in parallel. And then the currents that are consumed are not the milliamps or the microamps, but now the nanoamps or the picoamps of right? So you get picojoules and pico watts of power, right? So that's and so if now you look in biology, you also have this beautiful subthreshold domain. So subthreshold basically means you have conductances or currents that exponential in barrier voltage. In this case, this is the membrane potential here.
So what are the axes?
Right. So the axis here, the horizontal axis, this is your membrane potential. The membrane potential. So here, right, and the vertical axis on the log scale is your conductance of those ion channels. Those ion channels lost through this membrane. The membrane is ideally insulating for your cell, but the ion channels allow transport of ions going through, and that is governed by this. Those are proteins, and they fold based on voltage. So this mechanism, this Boltzmann distribution arises from how those ion channels will unfold, right, as voltage rises. And so you get this subthreshold domain here, if you want, right, of where you get this high dynamic range of conductances owing to this ion channels opening and closing based on voltage, right? And this is part of the excitability, say, of what say your sodium channels or your potassium channels are doing, right? And that's will give you excitability in right. Now, yes, you were going to say something.
Make a comment here as a
Yes.
peanut gallery. By the way, anybody notice the scale here? Can you read that? Do
Yeah.
you see? I have to ask as though you were students in a class. Do you guys mind if I do this?
Yes, I was going to say the same thing. Yes.
Slope of that curve there.
Yes.
You see the slope of that curve?
Yes.
What's the slope there? About 4 millivolts per changing the current by a factor of 3 per E fold.
Yeah.
But it only takes 4 millivolts to change the current by a factor of 3. Is that weird to you? Because what's the thermal voltage? The basic thing is the thermal voltage, right? Everybody know what the thermal voltage is, like 25 millivolts.
Yeah.
But it only takes 4 millivolts to change by a factor of 3.
So
How is that
yes,
possible?
Yeah.
If this thing's rolled by Boltzmann statistics, its slope should be basically the thermal slope, 25 millivolts. Or in the case of transistors, because the gate's not perfect, it only controls the channel partially. It's like 40 millivolts per E fold. But biology gets 4 millivolts per E fold. It's really remarkable. How is that possible? I mean, I know the answer, but how many people know the answer? Does anybody know the answer in this room? This is bad.
well, let's give it.
a lot of different
Yes, let's give one hint, right? So what is the thermal voltage? KT divided by Q. So KT, K is the Boltzmann constant, T is temperature. So KT is energy, right? KT is the energy that
It's
thermal
the
energy.
voltage that an electron has to fall through to pick up the average thermal energy.
Yes, I mean, in fact, this is Einstein's fluctuation
Yeah.
dissipation theorem, right?
there's fluctuation. There's KT is the fluctuation, right? That's the energy, right? Now Q in the denominator, that is a charge of your electron or your hole, right? And so right, and so the exponential is governed by that. KT over Q, that's the voltage by which your exponential goes, right? So each E-fold, you get KT over Q. KT over Q, if you work it out for an electron or for a hole, right? KT over Q is 26 millivolts at room temperature or body temperature. Now, so this is,
In other words, if you had
Yeah.
a transistor, I have to draw here, a
Yeah.
transistor slope would be like this. It would have shitty transconductance compared to biology, right? That's how biology is able to get away with a 100 millivolt power supply, because the devices are so steep. You know, there's no hope for silicon to get down to 100 millivolt power supply because the transistors just don't have enough transconductance. They don't change their current with voltage enough. But biology does this amazing trick. So I'm just asking, how do you think it's possible, given this ion channel, that this is possible?
let's give a hint.
Yeah,
So
just,
let's
no,
give a
I
hint.
don't want to give a hint. You know, honestly.
Yes, Yes.
It's not the ions flowing through the channel. If the voltage acts on this.
yeah,
core,
but correct, yes. They're not electrons and holes. The
They're
transferred
actually
are
ions.
ions. Okay, so what is the valence, say, of potassium or your sodium ion? 1, right? So the same. So by that token, it's not so still, right? We're not there yet.
Just think about it. We have, yeah,
But now what else is happening? Sure, that's
the
a little
channels open or close in a binary way. They don't change their conductance in a negative way. Some fraction is open, yes,
Yeah.
but somehow magically, the pores are able to change their conductance probability states in much steeper than as though they had one charge on.
I think Leo may have an answer here.
Multiple charges on, which they have.
Yes.
Probably a wrong guess, but if this is modulated at some rate, you change the duty
That's
cycle.
not it. That's not it.
Okay, let's think of the following way, right? So what would be your effective Q, the charge in the denominator of K over Q? If now it's going to be about four times greater.
This ion channel is now isolated.
Exactly, yes, the ion channel is, yes. Yes,
Exactly, you got it.
Good, great.
Charges in this. In this thing, it's a really complicated structure, you know, with thousands of atoms in it, that's built by, you know, the magic of biology, which we don't have in silicon. There's multiple charge sites in here that the voltage can act on. They all act in concert. You know, how you build a transistor like that, nobody knows how. Right? It's not possible because what's acting on here, it's different because here you're acting on the electrons in the channel. Here you're acting on the things that conduct the current. But yet Carver stretched this analogy to the entire field of neuromorphic engineering. I'm saying, you know, just this idea
so-
that you rule by Boltzmann.
the premise is, it's called correlated transport, right? So it's not a single ion that makes it through at any given time. In fact, there's 3 or 4 ions that have to go together.
The charges in the pore itself.
Yes, exactly, charge in the pore, yes.
You can also get tunneling too.
Oh, yeah, yes. Okay, tunneling, we'll get to tunneling, yes. Was another,
Yeah, can you run me through that again quickly? I didn't quite get it. So you're saying inside the pool, there's lots of different sites, which are kind of like lots of channels? Or
in order for that, yeah, there's multiple gates that need to be, and that could be another lecture some other time, right? On the Boltzmann. Yeah.
Interpret it as much
No, so you would imagine as something that senses this voltage here, amplifies this senses this gate voltage, amplifies it, and then applies it to the gate. Right. Like it multiplies the effect of this gate voltage. That would have a similar effect, but you know, it did more
Yeah.
devices.
So in any case, biology outsmarted solid state physics. And now the latest, so some designers or some electron physicists, right, or solid state physicists, they're trying to increase the slope by all kind of tricks, negative, or whatever, charge, negative capacitance, right? But yeah, so biology operates at power supplies. There's like 100 millivolts. The best you can do with silicon today is like 500 millivolts or so, owing to the fact that, yeah, the slope is a lot steeper. You can have much greater contrast for the same voltage, right? In in biology than in silicon by a factor of 4. So the power supply, that's why the power supplies in biology, this reverse potential, sodium and potassium, right? That difference between this reverse potential is about 100 millivolts, right? So that already gives that a bit more than 100. Yeah, no, 50, yes, yeah. Yeah. Okay, that's kind of a, now you may, okay, so that's where the field started. And indeed the first circuits that we were doing, so Cauwenberghs, he was at UPenn when I did this work, but there was a whole generation of, in fact, Misha had one of the first silicon retinas.
The very first one, but it was
Yeah.
very primitive.
Yeah, yeah.
Used to get spikes off.
Yeah, but so here's a very beautiful one that Cauwenberghs and his students were doing at UPenn. And so here you see, right, you have those photoreceptors and then other circuits around it. So physically emulating then the conductances, this lateral conductance here for the horizontal cells and then vertical cells, American cells, etc. Right, and then here your retinal ganglion cells, and then you have this on surround, on transient, off transient, off surround, right? A different
Sustained.
sustained. So, yes, sustained and transient. Yes, yeah. Right. Those are all right. So building circuits that take advantage of the subthreshold dynamics of conductances, continuous time, all right, and on the focal plane, and then you get this important thing. So the retinal ganglion cells, they will transmit spikes over the optic nerve, the rest of the brain. And that's an example of a very efficient code, a temporal code. Spikes are being transmitted, right? And those spikes will correlate both with spatial and temporal activity. The fact that we see the world around us with just about a few 100,000 of those fibers, right? In the optic nerve, firing at most, say, 100 hertz, typically less than that, shows that, I mean, what is that? A few tens or tens of megabits per second, right? There's an amazing compression that's being done on the focal plane, both spatial-temporal compression, so spatial, basically this on-off kind of things, so this local contrast, temporal, right? So this temporal contrast and then the spikes are transmitted the rest of the brain to optic nerve, and that's how we do all the processing. So that was an important realization. And much of the initial work in the neuromorphic community has been geared towards building really great sensors, right? And then have that spike domain, this temporal code of those events being encoded as spikes, as then the workhorse for doing further processing. Here's some other work with Ralph many years ago, but and we call that, those are change threshold detection. So now they're also called dynamic vision sensors, right? Those are so Toby can give a great tutorial on this in some time. But yeah, so the concept of there's no need sending any data if nothing changes, right? And so you can define a certain threshold, contrast threshold, and you only have to transmit that on or off event when it happens, right? And you can actually really see what's happening just from those on and off events, right? And this can be done very efficiently. Here's one implementation that we did. Just you take an APS, a standard active pixel sensor, add a few more transistors, right, to it, and then there, voila, you have your temporal coding. This can be made even more efficient, down to 6 picojoules per event. That's some latest work with Gert Cauwenberghs, who was also a Telluride attendee several years ago. But yeah, so that, and so the whole field of event-driven cameras, right, has been taken off and has been a wonderful addition to the field of computer vision. But the key here is that, so the world is then, the analog world is transformed into a world of spikes, temporal events, and then you can do processing, further processing of those temporal events, the spikes, right? In what you can basically emulate the rest, right? Cortex, basal ganglia, and all, right? And so there, the address event representation has been a workhorse, right? You realize that, yeah, you don't have to just make physical wires between two wire entire brain. That's not possible. You have 10 to 12 neurons, 10 to 15 synapses. Clearly, not every neuron is connected to every other neuron. You get sparse connectivity, and you also have sparse activity. So it makes sense to take advantage of the sparse activity and sparse connectivity for actually building networks with virtual connections as opposed to with direct wires, right? And the brain is also organized in that way, right? You have the white matter of the brain and you have the gray matter. The white matter is about connectivity, long range connectivity, and the gray matter are the actual synapses, right, where you have this local dense connectivity.
Does everybody understand what this means, address event?
Okay, address event. So I haven't said it yet. So address event stands for you encode. So when a neuron spikes, right, you encode that as an event by just transmitting instantaneously the address, the unique address that each neuron has, right? And so that if there's sparse activity, right, let's say you have 1 million neurons and they fire about 10 hertz, right? So that's going to be a total of 10 million events per second, and that can easily be transmitted over a shared bus, an asynchronous bus, right? And so then the address is put in the bus each time neuron fires. There's an arbiter that takes care of all that, right? And so that works nicely for transmitting the information, right? From one chip to another chip, right? That is point-to-point connectivity. We can do better than that. You can also then go to look up when a neuron fires. Not only do you transmit that events, you can also go to a table and figure out for each presynaptic destination when a neuron fired. You go to a list of postsynaptic destinations in the data field of your memory, with also parameters of the synaptic strength, and then just crank it through, right? So this is how you can then construct, in principle, any network as a reconfigurable system. Any network with synapses that are dynamically instantiated and that are basically stored in memory, in this case in DRAM or whatever it is, right? So that's been at least an early premise of how you can then make large-scale reconfigurable neuromorphic systems, right? And you can even do synaptic plasticity in this address event domain, because now we can actually change entries in the table here on the fly. You can even wire things, right? You can do plasticity that is structural in addition to just the change in the magnitude of a particular connection, right? So that's basically the field of much of this event-driven computation. Just a few highlights of the cognition, because that has been more the last 20 or 10 years of the field of neuromorphic computing, is the realization that, sure, for many years, right, AI has been, and so here, the vertical axis here is machine complexity, the horizontal axis here is task complexity, right? There's a cost of, on the vertical axis of the compute, and there is what you accomplish with it on the horizontal axis, right? And so on the log scale, the harder tasks you have to accomplish, well, so with traditional AI, if you want an exact answer, even with dynamic programming, right? If you want an exact answer, you have to still search the whole space. And so that the best you can do is at least linear, right? So that you get a linear penalty. If your task is 10 times more complex, 10 times more compute needs to be done, right? And it gets even worse, right? In traditional, case AI. So that was old school AI, right? Now there came along, and so that's, and there you get the curse, you get the curse of dimensionality, right? That's what it is. So things get worse when you have harder problems. And typical tasks, what we think is easy, is hard for computers. What is easy for computers is hard for us, right? Of course, we wouldn't trust our brains for doing our filing our taxes, and we'll let just whatever software take care of the Excel sheets, right? So that's going to be simple task up here. And there, sure, use your standard digital compute. But for hard tasks like just navigating and a fly just navigating and avoiding the swap, it's a really hard task, and is able to do that with a few 100,000 neurons. So it's a very hard task for computers, but it is easy for brains. And so there's the contrast here. What John van Orme was pointing out is this massive parallelism that really gives you scaling advantages. Think of this as turning the curse of dimensionality into the blessing of hyperdimensionality, right? By doing approximate analog computing and massively parallel, redundant analog computation, as opposed to basically pattern matching, as opposed to doing this very crisp if then else kind of sequential rules in digital. Right? Yes.
If we had to plot like different brains, like insect brain, what would that curve look like?
Oh, very good. So you would have I would postulate that it's going to be on this curve here, right? So we get here's a fly, say for instance, and the humans are probably over there, right? Dolphins may be up here, but yeah. So it'll be.
You don't know how to compute that test, that horizontal axis. It's already computed, right? For a fly, what is it?
Well,
Now,
the
what is
task,
problem? I don't know.
well, yeah, what can a fly accomplish, right? And if you can
Yeah, but how do you
quantify
find
the vision problem, right? So, yeah. But the point I want to make here is that so there are two important aspects here, right? So one is, yeah, you want to be able to abstract lower dimensional representations in the world. And that's the task of deep learning. Deep learning abstracts from this complex world lower dimensional representations. But at the same time, you need to be able to at least get to a level of complexity of human brain. Otherwise, evolution would have pruned our brains to a smaller size. And so if you want to do hard tasks at the human level of intelligence, you need neuromorphic computing to at least get to a level of, what is it, 10 to the 15 synaptic operations per second, and about 15 watts if you can do it, right? And so, and those two aspects will decompose nicely, right? So energy per task, minimizing energy per task decomposes in energy per operation, and that's what neuromorphic computing can really take care of, right? So very efficient way of doing this computing memory approaches. And then operations per task, and that's where deep learning, right, can then minimize the work that you do algorithmically for achieving a certain task, right? And actually neuromorphic has contributions in both directions or in both aspects. Device level here, and then is mostly algorithmic and inspiration from how the brain does the compute architecturally here. But yes, in any case, this requires a great synergy between engineers, nanoscience, physicists, right? And then neuroscientists, computer scientists, and cognitive scientists to handle those two complementary tasks. And that's why we're here, right? So when the field started, it was very closely tied to the physics and devices, and so now so the latest advances are more also cognitive, and there's been infusion of cognitive scientists, the computer scientists in this workshop, and that's for a good reason. So in order to solve this hard problems, coming up with brain level intelligence, it requires it's a really big effort that requires a large community, right? I'll just skip most things here, but so here's an overview. It is not the latest, but so for large scale reconfigurable neuromorphic computing, the ones where you can change the architecture on the fly, where you can actually adapt, where you're not stuck with one particular network, but you can, in principle, implement any network topology. So those are typical chips that have been done. So those are all reconfigurable, which means you can reprogram the connections, and also large, right? So at least a few hundred or 1,000 neurons. You recognize, so the brain scale, so let's start with the digital ones first, right? So Spinnaker has been out there for a long while, and there's a new version of Spinnaker now, Spinnaker 2, and we'll hear about that, right? So Christian Meyer will be here later. Intel, then, you had IBM True North, right? And now there's also next North Pole system. In fact, still the largest system with 1 million neurons on chip. Then Loihi had this, Intel had this Loihi, now Loihi 2. Again, right, there's large systems. Those are digital, and they're also analog or mixed signal implementations. So Cobena had the Neurogrid in Stanford several years ago. Heidelberg had this facet brain scale system, also analog. There's also, we had IFAT, several generation of integrated fire rate transceivers. And then in INI, Zurich, so ROLLs, and now DINAPs are also this large scale learning processors, right? Right? How do you quantify now what they do? So they can do a lot of things, but in terms of efficiency, you can then model energy per synaptic event as the efficiency metric, and most of those are in the order of tens of picojoules of energy per multiplied cumulate. So that's about roughly 4 orders of magnitude worse than the human brain. But still lot better than.
How do they compare to commercial CNN accelerators?
Yes,
That's
now,
more interesting than
Yeah, yes.
comparison, right?
so now the comparison that we made, right? So if you want to get a lot of DRAM access or even, so that was about nanojoule. So accounting for the fact you still need to get, so even the cost of going to your, well, actually, no, I'll take it back.
It's the more
Yeah.
complicated story.
The more
but I'd like to see
yes.
comparison
Yeah.
against the MediaTek,
Yeah.
accelerator.
But in any case, we want to make progress. So this is definitely not
Yeah.
we're not happy with that. And another important thing to realize is that it's not sufficient to take care of the gray matter, the crossbar array of very efficient synapses. So it's important to take care of the connectivity, the white matter. And so then you want to have both flexibility, right, in which you want to, in principle, you want to be able, every neuron to be able to connect to any other neuron, but this to be in expandable fashion. So you can't just have a flat architecture, right, where you have one crossbar for the entire, I mean, clearly you can't do, with 10 out of 12 neurons, you can't do a crossbar that's 10 out of 24, right? That doesn't make any sense. And so you want to have this hierarchical structure, this is with the white matter, right, where it can have this small world network as opposed to a flat network, right? And so that is what hierarchical additive event routing is about. There's some other ones out there here. But so let me just highlight the hierarchical additive event routing. The principle is very simple, right? So that so now you extend this AR framework to a truly scalable one that now can take advantage of large, yes, I guess, small world connectivity, right? So rather than having this spaghetti network where you'd have implement all those connections physically, now you can have dense local connectivity for all the local connections, but then for longer range connections, right, you hop up in the architecture. So then the event the neuron fires, that event is transmitted one level up, and then there is communicated to its neighbors, right? And so an event can keep going up in the hierarchy as far as it needs to go, depending on the longest range connection that it needs to serve. And then fan out only happens on the way down. So on the way up, right? So there's zero fan out, but fan out then happens on the way down, right? And so the greatest fan out is then at the leaf node in your architecture, right? At your destinations, right? And so then you have this very efficient, dense local connectivity, crossbar arrays at the leaf node in architecture. And then you have this white matter fabric of having events transmitted through entire architecture in this scalable hierarchical fashion, right? And so that's hierarchical additive event routing, complemented then with analog circuits that can do this integrated and fire array transceivers, right, that we call them, implementing basically synapses and neurons, dynamically associated synapses, and the neurons, because multi-compartmental neurons, right, in this case, 2 compartments, in analog, and then when with analog continuous time memory dynamics, and then when a neuron fires, it sends an event out. When an event goes out, right, as an AER event, it goes to these tables, figure out connections to all the other neurons, and that those are events that go back into this IFAT, as well as other IFAT chips, as events will basically propagate through this hierarchy of connectivity that we have. So that's all great, except power-wise, this was consuming about still 20 or so picojoules per synaptic operation, due to the fact that you still have to go to memory here, local memory, but there's still DRAM memory. And so now clearly, if you want to make this, you want to go to computing memory. Well, it just turns out that a synapse has a nice analog in the latest emerging memory technologies, whether you call that RRAM, resistive RAM, random access memory, or PC RAM, phase change memory, or magnetic RAM, right? Those are all the latest non-volatile large-scale memory technologies that are now replacing DRAM. They're non-volatile, but also fast, right? And they're
A long way from replacing DRAM.
they're still a long way. They're still a long way, but they're getting there, right? But the important component is they're conductance based, right? So you can think of them, so you can activate like a word line. So you can think of a presynaptic action potential, right? That will activate that conductance, and then you have your you integrate then currents, right, on your dendrite, and so then there you can make those crossbar arrays, and the whole field of, in fact, the second wave of neuromorphic computing, as it's called today, has been those crossbar arrays of RAM, resistive RAM, which are also sometimes called memistors technologies, right? Where we can even do things like spike time independent plasticity, right? We can also then adapt those conductances based on in rows and columns, right? Based on the relative timing of spikes. Yeah. So here, yeah. Now, how you do it? So you have to somehow transport. So now you can turn entire problem of learning to be totally local, but with this hierarchical additive event routing framework, right? You transmit your presynaptic event to your postsynaptic destination, right? So you actually, you port, right? So you port that event, the presynaptic event all the way there. So now, right? So right? So you have at the crossbar, so now if you have a core now, right? Let's say you have an array of cores. Each core will serve, say, a number of neurons, 2 of the 6 neurons, say, for instance, right? And so then you have both the presynaptic and postsynaptic action potentials available right there at this core. And then you can do local learning because all you need, so now, right, whether it's STTP or other learning rules, every learning rule is somehow related to the presynaptic and postsynaptic activity, right? So then there's no need for further porting activity, right, in network. Did that address the question, Chetan?
I like it.
Looks like you're adding extra clubs.
Yeah, yes,
So
yes.
is the benefits?
Yeah, exactly. Yes, the white matter. Oh, yeah, and the important observation: the white matter doesn't change. Is not plastic, right? The white matter is basically constructed through development, and it's the gray matter. It's the synapses, right? The leaf node in architecture. Those are the ones that actually adapt, right? So yes, you only would adapt your crossbars, and then the communication fabric, right? The network on chip that gets events across entire. Right, so those routing tables, those are fixed, and you don't. In principle, we can change them too, but so you leave them, and so then this is how you can implement scalable, large-scale neuromorphic computing with also plasticity that is now local, right? And that basically, I can just go. So basically, we have this chip. I'll just in the interest of time. So NeuRAM, I guess neuromorphic random. Or I guess resistive random access memory, right? And so we had this first an ICC paper, but basically this concept, right? So we're going to have just this crossbar array on top of an array of integrated fire neurons, right? So you have 2 of the 6 neurons, let's say 16 by 16, an array of 16 by 16 neurons, right? That and then you have a crossbar array of 2 of the 6 by 2 of the 6 synapses on top of it, such a way that each neuron connects uniquely to 1 row and 1 column of your crossbar array. And you can actually flip the direction. So you can choose what is the action, what is your output, right? So you can redirect the flow of this crossbar, and I should have mentioned, the crossbar array is an efficient way of implementing a matrix vector multiplication in parallel, right? So you implement, say, inputs along columns in parallel, and then you read the currents in parallel along rows, right? So that gives you directly your connectivity of your network. But this can be reverted, but you can swap them locally for each neuron the direction of this flow. Basically, either column in and row out, or vice versa, right? And this allows to do things like this allows you to backpropagate. You go back in the network in the opposite direction from output layer to input layer. That's what backpropagation does for a very efficient learning. But also autoencoders Boltzmann machines take advantage of this GIP sampling where you go back between input and output layers too. And so at great efficiency. I'll just skip the circuits. But yeah, this Boltzmann machine or other variation autoencoders, this is now generative modeling. You can do Bayesian inference in those neuromorphic networks, right? Where you take spikes as samples of distributions, right? And so then you can do Bayesian inference is also the workhorse for much of the latest large language models, transformers, etc., right? Or stable diffusions, another, right? You need noise anyway, and so it can take advantage of this probabilistic representations of neurons, spiky neurons that are actually drawing samples from distributions, and then you have those energy distributions, those Boltzmann machines, right, or Boltzmann energy landscapes. In which you can then train your network. GIP sampling is a way where you can go back and forth between, you present an input, so you do bottom up and top down. So bottom up, so you present a certain input, an image, say, right, and you occlude it, right, so then you can recognize it by basically in your inference is basically going bottom up. Sorry, the axis is reverted here. Here the bottom, here is the top. And then generation is the opposite, right? So now you can, so not only can you classify, but you can also then generate samples from distribution, and generation also allows you to clean up, let's say occlusion or missing pixels that you have, and now so that's in stable diffusion. You can dream up. You ask a certain vector here in the neurons, and now you can dream up is an image of what you wanted to see, right? And so here this is in operation, in virtual operation. This was a demo that Weyer1 gave at ICCC. So you take an image of a 6, you occlude a few pixels, then you ask it to recognize, but also then you regenerate that so by doing GIP sampling, right? And this is all done at very low energy, nano joules. So we had on the paper in Nature where we then demonstrated now you have a core, not only a single core, but now you have an array of those cores, 48 of them, and now you can do reconfigurable computing by configuring those cores dynamically for doing all kind of computation. So, and here we demonstrated that we're able to, and so very often you have to choose in neuromorphic computing, choose between great efficiency with a dedicated processor, and you can do one thing well, or you get great, it gets programmability and you can do anything with it, a GPU or an FPGA, right? But then you pay a price in efficiency. So here, this is showing that you don't have to choose if you can have really great efficient implementation at the core level, and then you have this dynamic architecture around it, right, where you can just route events, right, between cores, and then configure those for a particular task, right? That can be done after the chip is fabricated as a reconfigurable system, and they can even tune the systems. You can do chip in the loop training, right, for getting a really great efficiency and also accuracy, right? So this shows that yes, by just training one layer at a time, you program one layer at a time, and then you retrain the network for the remaining layers to then accommodate any imprecision that you have in the previous layers by taking advantage of the degrees of freedoms that are left in the subsequent layers for then readjusting the weights there. And you still only have to program each weight just once, right? Because now you retrain the network in the process of the subsequent layers. And so then you can recover most of the accuracy that you lose in this analog implementation of the network. And actually, so this stochastic computing is actually great. And in fact, the brain is very stochastic. Synapses fail about 50% of the time or more than that, right? Synapses are very stochastic. They drop out or they drop connect at the rate that is 70% or so, right? And so AI also has realized, or modern AI has realized, hey, doing drop connect or drop out during the training process actually will improve generalization performance because you emulate, right, noisy distributions that can account for greater variations in the inputs too. And so, yeah, you can definitely train networks with noise, but also do inference with noise then that matches that noise during the training process for doing more efficient computation. So stochastic computing is also a good direction for neuromorphic computing. I'm over time, so but in any case, you can also do just in a nutshell, short domain computing allows you to even get greater efficiencies by recycling the CV squared energy that you have in a crossbar array of now charge coupled elements as opposed to resistor elements. Resistors dissipate energy, right? Resistors, Ohm's law, I mean, you dissipate power for resistor. In a capacitor, you don't dissipate energy as long as you can recycle it by coupling that capacitive energy with an inductive coil on the outside. And if you do that, you can actually, you can do the computation where you move selectively charge, right, from an input line to an output line based on what is, right, based on the input here and whatever stored here. If you couple all that entire array of these elements with adiabatic energy recovery logic, right? Basically, where you have a hot clock, and then basically do processing based on you never close a switch unless the voltage across is 0, and then you can recover all the energy, coupling all the energy from your capacitors on doing computation on chip with an external coil, and then at resonance between capacitance and inductance, then you can recycle 90-some% of the energy, CV squared energy, and this I can get like a femtojoule per Mach of computation. We have a community where we interface everything here, and so we have this higher spike system that is available for the community. Right now, only a single core is available to you, but so the bigger system with 1,300 cores would be 160 million neurons and 40 billion synapses. And that's one of the systems that you can all access through the Neurosciences Gateway. You can write your Python script on your laptop, run it locally, or then you can run the same thing then on the hardware accelerated, right? That takes advantage then of the acceleration you have of the FPGAs that do the same operations there. And that's it. Thanks. Way over time, sorry.
Yeah, we'll start up again in, let's give us 20 minutes. So we'll start up again at 10:35. Optical telescopes where you can look, but optical telescopes can really only look at one thing at a time, and they're really subject to weather. So you really want to find ways to do it more efficiently, quicker, better, and in more places. And neuromorphic cameras and event-based and event cameras are really good at doing that. So yeah.
Radar is good for range, but how do you get the position from radar?
Phased arrays. So they usually have big phased arrays, but most of these things run like a fence. So they have a long sort of fence that just detects if anything passes overhead. So that's what they call it. The space field's not very creative. It's called space fence.
How much do those radar installations cost?
Millions, tens to hundreds of millions. And they're also very active. So you're just, throwing radio waves everywhere. Interestingly, there's some passive techniques as well. So there's passive radar where you can like take a radio signal from a tower and have it bounce off a satellite and measure it. And there's a great company that we actually work with in Australia called Silentium who do this. And they listen to radio stations bounced off the ISS. And they got into trouble because they work for the government. And they would call the local radio station to request songs because heavy metal works better than light jazz. And they got in trouble for doing that because it was leaking information apparently. But there you go. That's a cool little anecdote. Yeah. So that would be passive RF. So that's when you go, well, that's sending data to Earth. If I listen to what it's sending and see how that signal changes, I can figure out what it's doing. That's one way to do it. The other way is to look at other radio waves bouncing off it. That's passive radar. And then radar is when you send the radio wave up to bounce off it.
What about collision detection? So passing in front of the sun or in front of another radiator?
That's an excellent point, and that's something conventional optical sensors can't do, but we absolutely can. And occlusion detection is a hugely important field. So yes.
Pretty wide spectrum, everything from visible through,
Absolutely. And then transits are really interesting as well, but we're not quite at the point where we can use transit as much as we like, but absolutely, that's the right way of thinking with these cameras. David.
So maybe a year ago, there was an eclipse visible in New Mexico, and I was looking at the eclipse for the event imagers, and I'd see occasionally like things streaking across the field. Do you have any idea what that might be?
So, I mean, we do a lot of this. I've got bad news for you. It's probably insects. These sensors are amazing insect detectors. We saw lots of streaks around the moon, got very excited. They turned out to be insects.
Were they moving very straight, the insects?
Yeah, so that's the problem with insects, especially when you have a narrow field of view. They often move very straight across. But ultimately, you can see satellites near and around the moon. It's much harder. But what you're seeing most of the time, unless you're very certain of it, is insects. I got very excited and very disappointed because they curve.
Side by side, and the parallax, even if they're like 50 centimeters apart, is enough to tell you whether that's something that's hundreds of kilometers away, 50 meters away, or 5 meters away. Gotcha.
And just to that point, I'll go back to the first slide I showed, and you'll see two telescopes, and that's often why we have two. Yes.
Is there any high frequency information, what you're saying?
Yes, and I'll talk about that in a second. So yes, the fact that we have this high temporal information really does pay off.
Sorry, I'm asking if there's drones in space and detecting radars.
No, but there's
If there's some movement in the object or some aspect of it.
exactly that. So when we're looking at this object, we don't just see where it is, we see what it's doing. And there are this is really the most important thing. We will never be as sensitive with an event camera as you can be with an integrating sensor. It's physics. If you're collecting light, you're going to see more dimmer things. But when you integrate, you lose any temporal changes during the time you're integrating. And that's where the event sensors really have a benefit. And combining the two sometimes gives you the best of both worlds. But the important thing is if you don't integrate, you can move. And when you move the sensor, that's when you unlock all sorts of things in telescope astronomy you absolutely can't do with a conventional sensor. And in fact, when I started doing this work, I knew nothing about telescopes. So I would go to an observatory, put the camera on there. We couldn't see anything. So I tapped the telescope to induce a bit of motion. And my advice to you is never go to an astronomy observatory and do that. They will kick you out so far. But the difference is that it's a whole different way of operating the sensor because the sensor is different. And that's really what I'm going to talk about now with the astrocyte, because you can actually embody that in a whole system and do things very differently. So the long and short of this is that I did these experiments. They went really well. We did a slightly bigger one. I went to present it in the US, got some really interesting results from that. And then I came back, the Australian Air Force said to me, hey, Greg, can you come give a talk? We're really interested and we've heard some good things. We want to hear what you're doing. I come back and I go to meet these guys from the Air Force and I'm talking about this and they go, okay, here's a question for you. In 3 months' time, we're having an air show. If we had to do something cool to show them, what would you build? And I had a boarding pass in my pocket. I scribbled this idea of saying, let's put a telescope in a shipping container so that you can move it around because, you know, I used to joke that motion is good for us, so we don't have to be as stable. And the guy said, yeah, here's some money. I want it in 3 months' time. And I mean, we did it. And these are the astrocytes. So that's how it came about. Literally just, you know, someone asked me what you do and I was ambitious. So we built the thing and it was difficult, but actually the design that I drew there is exactly what we landed up building. And it all comes down to the fact that because we don't need to worry about motion in the same way, we can get around doing things in environments where conventional telescopes wouldn't work. Normally, if you want to do telescope observations, you build a building on a concrete pad, you try to get a bit away from every bit of vibration, make everything stable. We don't have to worry about that. Doesn't matter if the telescope wobbles a bit, if there's a road nearby, or if we're not perfectly level. The sensors don't worry about that. In fact, we can even operate when it's windy. So because you changed the way the sensor works, you changed everything about how you approach it, so we can make these things mobile. So we have bad bushfires in Sydney, there's smoke everywhere. Put it in a truck, move it somewhere else, and you can do imaging observations. And we can do interesting things like ranging, for example, if we have two looking at the same satellite. So we have two of these. One is in Australia, one is in the UK at the moment. And that's really to give you a sort of visual illustration of what this is looking like. This is kind of what each one can see. The trick is you can only look at one object at a time with a telescope, well, unless you have two in the field of view. And the idea is that if you have to move there, find it, stop, take a picture, move somewhere else, you're really taking one picture, you know, every couple of minutes. But if you can continuously move, you can pack a whole lot more observations in at the same time. And you can see things you can't normally see. So we're really looking, you know, you have to really worry about satellites being illuminated by the sun. So this really shows the field of view and what we can see from each one as, you know, between day and night cycles. And there's a tiny point where we actually overlap and can potentially see the same satellites from both hemispheres. So, yeah. Yes, that's exactly what it is. So it's the shadow.
What those green and translucent hemispheres represent?
I'm very colorblind, so I have to defer to Alex on this one.
Fields of regard that is accessible
To the telescope.
to the telescope, but you would only be looking at a tiny chunk of that space at any given moment. So that does tell you whether a satellite is going to be visible at all.
Okay, so yes, we have. It's not something we currently do. Weirdly enough, we had much more success with the older sensors, not the newer ones, and that's an interesting question as to why. The reason we don't do a lot of it right now is that if you pass across the sun with an event-based sensor with a telescope, you basically have a magnifying glass and you melt your sensor, and we don't have enough sensors to do that. So it's something that if we had more time and more people, we'd like to do. And in fact, if there's interest in this, we'd like to try some of that here during the day. So we'd like to try some daytime telescope observations with what we have, where we actually have the telescope on and we can make sure we don't look at the sun. So if that's something that's interesting to people here, that's a whole project that we can absolutely talk about. So come this afternoon during our sort of brainstorm meeting and we can talk about that as an option, because that's something really interesting if you can do it.
It's like a pinhole, you know, a aluminum part. A pinhole. Reduce the light.
You don't even need to reduce the lights sometimes. We never did that in the past, but we could. We can definitely see down to like magnitude 4 stars during the day. What we can do beyond that is the question. And, you know, there's a couple of them, but not that many magnitude 4 brightness stars. Yeah, bright stars.
Could you actually explain why you don't care about small vibrations, but
Oh, yeah, absolutely. Sorry, I should have probably been a bit clearer about that. It's because we have this high temporal resolution. So if you're integrating and you move, you essentially get motion blur. But because we don't integrate, if we move, the light just moves to the next pixel. So we will see the movement, but we have enough temporal resolution to capture that. And if you're looking at a star field, if there's anything that affects the telescope, like wind or vibration, all the stars will move. So if you get the global motion vector from everything moving the star field, you can cancel that out and just go back to a nice stabilized image, which is kind of what I'm showing here. The top left is the raw data captured on a satellite. And what you might notice there is everything is moving. The satellite is the object moving from right to left, and all the stars are moving left to right. And that's actually something we do. We call them balance speed recordings. We know that the stars are moving at a certain speed around as the Earth rotates, and we know the object is moving at a certain speed. So we actually pick a ratio between the two so that we know the speed of everything in the field of view. And that makes separating things really easy because we know all the stars are going one way, and anything moving at that speed in that direction is a star, and anything not moving in that speed in that direction is the thing we care about. And we can extract this. We actually label the events as stars and satellites using an automated algorithm. At the end of the day, you land up with this. This is kind of the output, and this is the sad truth of it. The people who care about space data don't care about neuromorphic engineering. They care about this. They care about the data that's relevant to them. So as much as I'd love them to go, oh, this is so exciting, it's neuromorphic, they go, that's really exciting because we have high temporal resolution, and mostly they're excited because they know if the object is moving left to right or right to left here, because they have the time as well. So when we capture this, we actually use the stars to figure out where we're looking. And here is what you were talking about earlier. This is actually a plot of the event rate for that object over time. And this tells us all sorts of things about the object. First,
Time scale and the vertical scale, I can't read it at all.
oh, sorry. This is number of events. So this is about 10 to 15 events. And this is in seconds up to about 30 seconds. I apologize. I can't even read it from here. I just happen to know. So this object is nice and stable. This object isn't. And you can actually see, this is actually the real events plotted in a stabilized frame. You can actually see that the object is essentially tumbling, right? So when we record it, we get these blips. And if you look at the event rate, you can see very clear, very periodic blips. And from this data, we can actually figure out how the object is tumbling in space. And because there's two peaks like this, it's probably tumbling around two axes, or it has a certain structure that we can use to tell what it is. Yeah. An event is a pixel change, a change in contrast at a specific pixel. So yeah, change in brightness, yes. Exactly, yeah. And this basically says, we now know all the change events that are connected to the satellite. How many of them happened in a specific portion of time? And that's really, really powerful information because we can now say that this object is tumbling. And if we know something about the structure of the object, we can even start telling you what axes it might be rotating around. And this is really data you can't get from an optical sensor. You don't have access to it. So this is really what makes us completely different from everyone else. And
Maybe you could quickly say about things when a satellite tumbles.
oh, okay. So if a satellite, yeah, that's a good point. Sorry. Please feel free to stop me and ask questions like this. There's so much assumed knowledge that I sometimes forget. So sometimes active satellites will actually position themselves in such a way so they're facing Earth, for example, or facing away. The Hubble will want to look at very specific things in space, so it'll be pointing in very specific directions. Communication satellites will always want to point down. But basically in space, you have to work quite hard to stay oriented on something. And I'll use thrusters and all sorts of things to do that. When a satellite reaches the end of its lifespan or something goes wrong, it goes out of control and it can start tumbling. And if it starts tumbling, it's essentially rotating around a random axis. And that's dangerous because it can actually affect how it moves. Yeah.
That could be my next question. So you detect pixel intensity, but what about color?
Yes.
And if you're looking at for the occlusion example,
Mhm.
you shield the visible light, you're looking at other ends of the spectrum, looking for frequency shift, looking for Doppler.
So we can't get color from the event-based sensors that we have at the moment. There are color cameras, but again, you'd be losing light because you have filters. So you don't want to do that. What we have done in the past is use two telescopes with different color filters to look at objects in space. And that's really interesting because the light reflected back from the object depends on the material of the object. So for example, if it's a shiny metal surface, it'll reflect all the light back and you'll get a balanced amount of events in both channels. But if it's a solar panel, for example, some of them reflect more green light and some reflect more blue light. And kept on tape, for example, only reflects certain light waves. So by looking at the ratio of events from the object you're tracking, you can actually start inferring what it might be made out of. And that is actually one of my PhD students' entire thesis. So it's a really interesting way to do it. And of course, if we had color event cameras, we wouldn't need to use two sensors.
You can get color without a Bayer filter. Okay.
I'd be really interested to figure out what we can do there. These are all things we'd love to look into because and then of course the next one is infrared, which we don't have yet, but it'd be a really interesting direction to move into. All right. Yes.
One quick thing regarding those curves. We have a bunch of those recordings where we know the satellite we're looking at, and we have the even curve for the satellite. So if anyone's keen to look at that, see if we can use machine learning, perhaps predict the labels based on the curve. That'd be a very interesting thing to do, see if we can recognize the satellite.
Yeah.
Based on those numbers.
And we have, I'm sorry, Alex, that was exactly what I was going to say. Actually, at this point, we have enough data that you can use, we have an enormous amount of data. So we can actually use proper deep learning techniques if that's something people are interested in. Yeah.
If it's tumbling, like if it's stable, does it see anything?
So if it's stable, I mean, that's part of the question that Alex is getting to. So this is very clearly tumbling, but we get a plot like this for every satellite we look at. And we have satellites where we have hundreds of recordings for them. It would be really interesting to see if there is frequency information in there that we're missing. So that is kind of the deep learning techniques Alex was talking about. We have the data, we just don't necessarily, we haven't had time to look through it that way.
Variations are probably due to atmospheric perturbations. But since we have the stars in the same recording, we might be able to remove that and see if there's anything left.
Well,
Exactly.
if you're looking at color, you probably do give us some information.
There's a question from the chat.
Okay.
Is being used to track meteors.
Yes, that's something we're really keen on doing. We just don't have as good tracking information for meteors, but tracking meteors with these, very much something close to my heart. And if anyone's interested in trying to find shooting stars, well, meteors and meteorites are different things, and hopefully one becomes the other. But if anyone's interested in meteorite and meteor tracking, please come find me. Really want to set up some experiments, do some all-sky cameras around that. That's another project that we can discuss today if that's of interest to people. Yeah.
One question is, it's with derailing your talk.
That's all right.
Do you have any algorithms here that you think are fixed enough that you think it might be worth looking at hardware acceleration?
Absolutely. Yes, a bunch of them. One of them that comes to mind is when we take the stars from here and we try to solve for it to figure out the astrometry, the plate solving, that's an algorithm that we would love to find a hardware application of. And there's some really compelling reasons why you want to do that, because that's not going to change for 100 years. So if you build a hardware chip that did that, it's got a good shelf life. So yeah, another topic to talk about today if you guys are keen.
Yeah, sorry, just to cut to the chase.
Yeah.
So question about training, an opportunity to train from some of the data sets.
Yeah.
Leads to the next question, which is, where's the money?
Where's the
Who's
money?
got the money? Is it funded? Is it other private institutions that are corporations that are paying for data or?
In terms of just,
sites?
you mean for the space situational awareness? I mean, yes, it's an excellent question. And it's a difficult, it's a horrible marketplace. That's the sad truth of it. No one knows what they want. They all know they need it. They don't know how to get it or why who's responsible for what. So ultimately, US government
You know, how safe?
is probably the biggest spender. Defense, because obviously they want to know where satellites are, but there's also a commercial interest. Space traffic management is the commercial side. The FCA or the FCC, I think, is now in charge of satellites in the US, and they need this data as well. So there's a lot of governments at the moment, but also if you're a satellite operator, right? Let's say you operate a geosynchronous satellite and something goes wrong. You may want a whole bunch of telescopes to look at it to get a sense of what's happening. So it's definitely an emerging market. No one's quite sure how it all fits together. And the ground-based stuff is important, but the space-based application of the neuromorphic sensing for this sort of thing, doing this from orbit is really the key thing, because you can essentially see all of space from orbit, whereas you can only see limited parts from Earth, and we get around that by moving our observatories around, but that's not as practical as just waiting for your satellite to go to the right part of
So your work right now is funded by Australia Defence.
It's all over the place. So this work has been funded by all sorts of things, from the Australian government to the US government to private industry to the university itself. It's a complicated arrangement, but yes, we have a whole bunch of these, and some of them can just be used for research purposes only. Yes. Right.
Space debris and crash.
Yes, absolutely. So most of what we look at is space debris, but so there's two real tasks in space. One is the catalog maintenance task. So there's a catalog of all the known satellites, and we have to update them because there's a lot about the orbits that change. So even though we know where it is now, that only really lets us predict it accurately for about 24 hours. So we need to go look at it again and make sure that we can measure the difference from where it is to where we predicted and update its orbit. So catalog maintenance is really going around looking at all these satellites and making sure they are where they are and updating them.
Why changing them? Is they're low or shallow, right? So they're hitting the atmosphere basically, and that's changing the orbit all the time. That's why it's not like the orbit of Pluto.
Yeah, well, actually, so Toby, you're half right. That is what affects some of the satellites, but you also got to remember that people move their satellites and they don't bother to tell everyone else. So, sometimes a piece of space junk just turns left and we go, oh, that wasn't a piece of space junk. So, everyone has to be sure, not everyone's friends in this world, unfortunately. So yeah, atmospheric drag is a big one for low satellites because it actually varies. and other satellites, all sorts of things can happen to them.
Do you have any problem if you accidentally like record the position of a spy satellite with the survey image? Is that something you have to worry about? Or is that like,
There,
you're not allowed to publish those results or anything
I'll-
like that?
I'll answer the question this way. There's a group of old men in the US who formed a club where they sit with binoculars on their roofs and find spy satellites. And they're still doing fine. So ultimately, the reality with that is that if we can see it, they want to know that we can see it. So like, there's no real restrictions around that. So like everything we do here is like, if we can see it, then they have a problem, not we. No, it's their problem, not our problem. But it's a good question.
Do you have any meteor data?
We might, yes.
One recording, but at least it shows that we can see them.
Well, one that we know of. We do have a lot of uncorrelated tracks that pass our field of view. Some of them could be.
Amongst the lenses that we got here, we have an multi lens, so basically 360 degrees, but 180 degrees. So we could try to experiment with that here and see.
It's gonna be a shower.
It starts on the 14th.
Oh. And are they visible from this part of the world? Well, I think we know what we're doing on the 14th then. Watch, it's going to rain for the 14th or the 19th. I guarantee it. If you want rain, bring a telescope. That's all I'm saying. We arrived and it rained for 2 days. Just pointing that out. All right. But this is good. So what I might do is I might go as far as I can today. So when we run out of time, we'll just put a pin in it then, and I can always have another one and I can talk more about the space stuff afterwards. Because the second half of my talk is really about saying, okay, now what happens when we go into space? And I might give you a quick overview of some of the space systems that are out there when it comes to neuromorphic sensing, give you a bit of a history. As I said to you before, we've actually had 2 space missions. So all the data I showed you is from the second space mission. The first one I did with Eunice W. Canberra a number of years ago. So it launched in 2021. It probably started in 2018. And this is actually, it was a really interesting satellite. It was a CubeSat. So CubeSats are really small ones. So this is to give you a sense of, it's like a bread bin size satellite, each of these. This satellite actually started off as one big satellite that would then split into 2 parts and then fly in formation. And then we're testing all sorts of things about that. Each of the 2 satellites, so the satellite was called M2, and when it would split up, it would have to become M2A and M2B. And both of those satellites actually had a Davis 240C on it, right? And they were to fly in formation and they would go capture data. We built the neuromorphic payload, they built the rest of the satellite. Things got complicated. As far as I know, they haven't actually turned on the neuromorphic sensors, and certainly we haven't got any data from them. But we did have the first neuromorphic sensors in space, okay? And as I said there, we had the fastest event-based sensors in terms of velocity relative to the ground. And this is actually a really cool photo. This is a real image from the one satellite of the 2 separating from a conventional camera. So that's really neat. So it would have been really great to have the event-based data from this as well. And, this is the thing I'm going to tell you over and over again about space. It's hard. It's difficult. Things are going to fail. No one takes you seriously unless you have a failed mission behind you almost. Yeah. Well.
So you know whether the GPS or the camera is going to be more sensitive to heavy versus 24 size.
Yes. I mean, the upshot of that is that the sensors that we have up there have been up there for 3 years, and they seem to be functioning just as good as they did when we first launched them. And Toby and I are going to sit down at some point during this workshop and look through the data and see if we can come up with a. Okay, but yes, this is something we really want to explore because we now have real data for that. So this was the first mission, didn't go well, and as I said, you're going to fail, but it was actually really important for us because we learned so much about how to build a camera system for space. It's nowhere near as simple. You can't just go and reset the hardware here. So everything we learned about doing that actually really helped us get a leg up on our next space mission. And the next one really is twofold. Oh, firstly, I should say this is kind of a meta sort of slide, but this is actually the M2 satellite with an event-based camera on it, observed from another event-based camera in one of our astrosites on the ground. So it's an event-based camera looking at an event-based camera in space, which I think is pretty cool. Oh, sure. This video over here. So I should say this, what we do now, because when you're looking at things moving through space, sometimes they're quite slow. And when we want to look at the data, we take about 30-second recordings. And just to make it easy to see things, we take that 30 seconds and we play it back in 3 seconds. And we play it backwards and forwards. That's the satellite over there moving.
What are the stars?
Those are stars. And that is something crossing our field of view. That could be another satellite. That could even be a meteor. So this is a very quick way to see what's in this recording. You can see the object that we're seeing is very clearly visible. There's lots of stars, which is why we can see all the stars that we matched over here. And this is moving across quite a lot of the sky because it's in a low Earth orbit. So it kind of flies across the sky, whereas if you're higher up, it's further away. So it'll take a slow amount of time. This is a couple of 100 kilometers.
And it crosses the whole sky in like 5 minutes, right, or 3 minutes?
In about a minute or two, honestly.
Okay.
So, you know, and then of course, here we get the information from it, but this probably is more atmospheric than anything
And
else.
your telescope was tracking it here, right?
Yeah, so whenever, well, it was moving so that we keep it in the field of view. So if we were tracking it perfectly, it would be stationary. And the mount can do that. But here we're actually moving, well, actually, I'm lying to you. We're trying to keep it in the field of view, but it's moving very fast.
Where it was.
So there's a catalog of all the satellites. So the US government maintains the best catalog. So we pulled the tracking elements for that, and that told us where we could then predict it to be. And what you actually, unfortunately, is cut off here. But we often, in fact, you can't see it here either. But there's actually a dotted line here that shows us where the satellite should be and where we measured it. And the differential between the two, that's what everyone cares about. That's really to say, well, we know it's there and we thought it was here. So we're going to update the orbit for the thing to make sure that it's now over here. And then we can propagate it from there to make sure that we can find it the next time. And that's why if you lose a satellite, it's so complicated. And as I was saying earlier, there's two tasks. The catalog maintenance one is continuously updating the known satellites. The catalog generation one is to say, I don't know, let's go look for new things that aren't in the catalog. Or like this thing that shoots through here, that may not be in the catalog. We have enough information here to figure out something about where it is, but we're only seeing for a very brief amount of time. And you have the aperture problem. It could be an object very far away that's small, big, or a very close one that's small. So you don't know, and you need to do multiple observations from different sensors to do it. So that's really the two problems. And yeah.
Spaceships going to the International Space Station.
No, we haven't, unfortunately. And we really want to see it from the cameras on the ISS as well.
Facial structures instead of
Andrew.
I can't recall how much interaction you had with them too. Were you able to ask them to maneuver the satellite for you?
No. So they dropped one of the satellites during testing and broke one of the event-based cameras. So we kind of knew one was going to work, and that was really the end of our amiable discussion. So I haven't heard anything about the satellite except for the fact that I haven't seen any data from it. So I draw that as, that's why we left it as awaiting commissioning, to be polite, but I think they're dead. I think we have put some space junk up there, and I apologize. They will come down at some point, but at least we know where they are, right? So just a kind of a cool aside, but yeah, we actually have lots of recordings of these. And if anyone has a favorite satellite, come find us and we'll actually sit down with you and observe it live from Astrosat, one of the Astrosat observatories if we can. So if we move on to the next space mission, this is actually the follow-on to M2. This is the one we did with the United States Air Force Academy. This is the one that's on the International Space Station right now. It's Falcon Neuro. It's a 2 Davis 240C cameras. And here it is going up on the SpaceX rocket. You can actually see it in the unpressurized cargo bay. So this is from the booster that's separating. And this part will go to the space station. We're on something called the Space Test Platform, which is something the US government runs. There are actually 2 of them on here. We're on STP-7. There's us over there. And actually, there was another event-based camera mission called Casper that was on the same satellite as us. So we went up together, and Alex and I were having a debate about which one actually got to space first, because it crosses the Cohen line, and then you're in space. And it really depends on the role of the satellite, which one of the 2 got to space first. But I think that's academic, because we actually had the first event-based cameras in space a year or 2 before that. Don't tell anyone that didn't work. And here it is. This is a real photo of the Falcon Neuro payload installed on the space station. It's not there anymore. It's been flipped, and now I think it's on the top pointing the other way. But it's been up there for 3 years, and it's produced incredible data. Interestingly enough, this over here is something called ASIM. That's a lightning detector that's on the space station. And they're actually working with those guys on potential future missions, because the primary mission of Falcon Neuro was lightning detection. That's what we were originally going to do. So lightning and high altitude sprites. So it's kind of fortuitous that we're in the same field, same position. Unfortunately, our field of views do not overlap. For our new cameras and missions, we're going to make sure that happens. In fact, we had to design the follow-on mission to look around ASIM, because it's now where we are. So, you know, there's a lot of politics and jostling in space. So if we talk a little bit more about the 2 space missions that are on STP-7, we have Casper over here. That flew a Prophecy Gen 3 sensor. The mission there was about satellite tracking. If you look at the satellite there, it has these 2 very big telescope-like protrusions at the top. it turns out those aren't the event-based cameras. The event-based camera is actually on the side behind that camera that goes in, and that's the field of view from the event-based camera. As far as we know, there's been no data from this sensor, unfortunately, but it would have been really exciting if it did. This is what we built. This is Falcon Neuro. Space stuff doesn't always look that glamorous, but essentially it has the two event-based cameras here. And it's been up for 3 years. And I'll show you some interesting data from that as well. I should just mention another interesting project is that you might have heard of Thor Davis. This is a European Space Agency project where they actually flew a Davis 346 to the space station for a Danish astronaut to use to look at sprites. And they pointed it out the cupola, which is what you're looking at there, and actually recorded thunderstorms and caught a fantastic sprite with an event-based camera. So if for those of you who might not have been here for yesterday's talk, sprites are essentially electrical discharges that go from a cloud up towards the atmosphere. And they're often really pretty to look at. I'll show you a really beautiful sprite recording in a second. But essentially, here's the thunderstorm and lightning in there, and the sprite forms above. And we really don't know a lot about them, and there's a lot of science and physics about that. This is artificially colored, but you can actually see the sprite there, and that's what they call a carrot sprite. So really interesting scientific outcome there. Really excited. We're actually working with them to see what we can do as follow-on missions, and then have some way of mounting one more permanently to look for these sort of things within the space station. So let me talk a little bit more about Falcon Neuro, because that's the payload we have. And I guess, as I said before, the primary mission there was to look for sprites. So this is what a sprite looks like. This is actually my collaborator on the Air Force Academy. He recorded this with a Phantom high-speed camera. That's lightning. It's spectacular. It's really beautiful to see. It's also extremely fast. And this is, I think, 100,000 frames a second recording. So, you know, you really got to be lucky with an event-based, with a conventional camera. There are so many opportunities to look with an event-based camera to see what we can see, because the more structure you can figure out, those leaders that you see there, those things that are moving around, I'll just play it again quickly. They can move at a tenth of the speed of light. And as a result of that, they're struggling, figuring out how they work and where the current is discharging in the atmosphere, really important for all sorts of reasons. So to see how these bits are moving and interacting, I mean, this is a particularly good sprite with a conventional camera, but of course, being able to do this from orbit is the holy grail of this, because this works really well on the ground where you can fill up a hard drive. But if you take a terabyte of data in space, getting that to the ground is the problem. So if we can do that from space, not only do we have less data to deal with a neuromorphic camera, but if you're in space, you can look down on the thunderstorms, which is much easier than looking up and trying to look around them. So that's kind of what we're aiming to do. This is Falcon Neuro over here. This is sort of the 3D construction of it. There are two cameras. One points in the RAM direction, so it points at the horizon in the direction of motion of the ISS. So it's like looking out the front window of the ISS. Yeah.
Sorry, I have one question.
Yeah.
How do you know, say you've got an event-based camera in
Mhm.
space and you're like want to see some thunderstorms.
Yeah.
How do you know when to point your camera at the thunderstorm and when to turn it on and when to track data? Are you using another sensor to check first, or how do you do that?
You don't. That's the problem. And that's something we learned from Falcon Neuro, which is that you can predict storms and you can say, okay, I think I'm going to move over a storm, but you really want an autonomous mode of operation where you can schedule things. And on top of that, you want something that can say, hey, I saw a big spike in the data rate. That's probably a lightning storm. Send that data down. So I'll talk a little bit about the operations of this and what we learned from this one going into the next one. This was more of a proof of concept, but you've hit the nail on the head there. You know, weather's unpredictable, so you can't predict what's going to happen and when.
And you need a way of automatically detecting, because if your thing's you're taking data all the time, you need a way of knowing where in your data you've captured lightning as well.
Exactly. And that is an extremely relevant and open problem. And if you have any ideas on how to solve that, that's something we could work on. And if that works, we'll put it on the instrument that's going up in beginning of next year, because that's entirely the missing piece, which is that how do you know if you've seen a lightning strike? And it's a hard problem because we don't know what it looks like, right? We now know what they look like from a Davis 240C camera with a small, tiny lens. What does it look like through a better optic with a better camera? So, you know, it's an interesting problem. Like taking the data from this is really important in sort of shaping how we approach the next task. But we're going to have to take data, look at that data, figure out what lightning looks like and how to detect it. And then the process of trying to update the algorithm on satellites, that's a whole mind wants to go into. So you really want to try to find the balance between making it configurable and making it so that you actually stand a chance of seeing what you want to see. Yeah.
So for your kind of applications, how far are we from simulating the response of the event camera?
Well, we did simulate a lot of what we thought the data from space would look like, and it looked absolutely nothing like that data. So There's no substitute for the real thing. And I think this is an important point that I can talk to, which is that you can only simulate what you know, right? So your simulation is only as good as the assumptions you make. And if you convert data from a conventional camera, from a video, for example, you're subject to all the limitations of the sensor that took it. So because these are different sensors in a vastly different environment, it's really hard to make informed guesses about what the data is going to look like. We tried, but we failed.
What kind of simulations did you do?
We did both video to events. So we took recordings of sprites and lightning from other sensors and converted them to events. Wasn't terribly useful. And we tried some modeling and sort of like camera simulators where we can actually model the 3D space. That was something our colleagues did. It didn't work very well. Again, you know, we just had no clue.
Still open.
Very much so. And I think we have a better handle on it now that we have some real data. Like we didn't know if we could see stars from the RAM camera on this instrument. We know that now. And now that we know what stars we can see, we can figure out how bright they are, and then we can get a sense of the performance. Because when you look at stars from the ground, you have the atmosphere. And that causes perturbations, which allow us to see stars sometimes, but it also causes the light to smear across the sensor. When you're in orbit, you don't have the atmosphere. So you have this trade-off between the fact that you don't have atmospheric scintillation to help you see things, but you can see dimmer things because the light is less blurred across the sensor surface. So you have to balance the two. I've asked. I've even offered to go and do it, but they've said no to both of those. So, all right. So, yes. So the one camera looks at the horizon in the direction of motion. The other one looks straight down at the Earth for Earth observation. Right. Both have amazingly interesting data that came out of them. And just to give you a sense as well, just how this came about. Right. This was pure luck. And again, my advice to you is talk to everyone about what you're doing, be excited about it, and follow up opportunities. I was at a conference in Colorado, actually. I was talking to a bunch of people. I actually had a stand, the Air Force Research Labs, talking about event-based sensing. And yeah, I do lots of weird hand gestures, as I discover, and in all these sort of photos whenever I'm talking about this stuff. But what landed up happening was someone said, hey, I know a guy who might be interested in this. And it was just a side conversation. I gave a talk at the Air Force Academy. I met some guy who spent his whole career trying to find people excited about sprites. He got me excited by sprites. He said, look at this thing. Do you think we could put some cameras in this? And I said, yes. And that's what's on orbit. So again, you know, none of this was planned. And because I went to him and I said, I've done something similar on those M2 satellites. It didn't work. This is what I learned. That was enough for him to go, I can work with this guy because he knows how hard space is. Like, don't underestimate how hard space is and learn from everyone who could tell you stuff. Everyone who's done it will tell you something interesting you didn't know. And like that information is golden. Don't like charge into these things because space is really hard, and learn from all the mistakes everyone else has made. So just to give you a sense of what an actual space instrument looks like, you tend to build at least two. One is the engineering unit on the ground and one goes in space, and use the one on the ground to test things out before you deploy them in space. As again, space hardware doesn't look all that glamorous. This is Falconeer. This is the engineering design unit on the table here. You can see it's covered in tape. You have to be very careful about things like openings like this. It's all, you know, to put things on the space station is actually particularly difficult because it's a crewed spacecraft. So there's all these safety restrictions and all these considerations that you wouldn't think about. Plastic doesn't do well in space. The vacuum can leach the doping materials out of semiconductors. So you have to be careful about that. You know, if something breaks, if glass breaks in space, that's a huge problem because it just floats around. If metal breaks off, it can become conductive. So you have all these sort of problems around that. So that's what the actual instrument looked like. Just to give you a sense, like when you put things in clean rooms, this is what you got to do. If you have a beard, you have to wear a beard guard, which is even more exciting. But this is, you know, you build the one as the test unit on the bench, then you have to build one in the clean room, and you have to go through all these stages and processing that we don't think about. And fixing things later on is so difficult. So you really have to do something that academics are not used to. So you got to make sure it actually works before you give it to someone else. So let me talk a little bit about something else. It's kind of a funny story, but Charlie is an Australian government initiative. It's like a STEM outreach program to encourage people to take careers in science, especially with regard to space. And this is the Charlie character. They made a couple little animated shorts about her. And we actually put Charlie in space by having her etched on the Falconeer instrument. Unfortunately, at one of the air shows, this TV got stuck on this image and everyone thinks I'm Charlie, which I'm certainly not. So for a long time, people called me Charlie and they still do. But I'm not Charlie, that was Charlie. And here it is actually etched onto the top of the flight instrument.
That Charlie will survive the rocket launch to space.
I can see they've just put some kind of cover over Charlie.
Thermal blanket. And this is actually what's on the space station. So Charlie's still up there. looking up. So, you know, fun little thing, but really, you'd be amazed at how many people really responded well to this. And I tell you now, the Australian government is far more excited about this than the actual data from the space station. So make of that what you will. I'll tell you another story, and unfortunately, Guido is involved in this one about the launch of Falcon Neuro. So Guido and I went to watch it in Miami, and we got everything ready. We got lenses and setups, and we were really excited for it. And we went down, it was pouring with rain. We couldn't unfortunately get to the official NASA viewing station because of COVID, but we made a plan. We found a little pier somewhere that we could see, you know, the launch site from. We were really excited. We made one small mistake though. So we had a laptop and we're watching the launch countdown on YouTube, and we're like, okay, cool, we're all ready. What we didn't take into account was that there's a 30-second delay between the YouTube feed and what's actually happening. So we were just mucking about with things. We heard a bang, turned around, and I wish these were our photographs. They're not. We didn't get anything from that launch. So just a word to the wise, you have to really think these things through. So yes, you know, an interesting failure. This is the best photo that anyone we knew took. And it's actually, you know, that is Falcon Neuro heading up to the space station.
And that they will survive the journey and still work once they arrive in space. If the cameras don't pass the tests.
As it separates from it, and that's off going into space. It's kind of a thrill watching this live, going, hey, that's my thing over there that we built. And yeah, it gets installed by a robotic arm. This whole payload is like a big pallet that gets pushed onto the space station with a big connector. So no, there's no, it's kind of amazing. They just use the robotic arm to take it out of the payload bay of the craft, and then they essentially push it onto a big connector. It lines up, and within 2 days we're operational. So there we are sitting over there. And I mean, space photos are kind of incredible in that way, but this is it being installed, and we were actually operating in a couple of days after that.
Towards the ground, yeah, it's on the bottom there, right?
Yes.
Okay, there.
It's that in that circle over there. So the nadir camera looks that way, and the RAM camera essentially looks that way because the ISS moves in that direction. And this is the Columbus module of the ISS. So
It's always lined up in that direction, in the direction of orbit.
mostly. So it's usually in this orbit. There are two exceptions. When the Soyuz comes to dock, they flip it around so the docking port for the Soyuz is in the right orientation. And when the Russians send up a new module, they sometimes spin the space station around by accident for a couple of times because their boosters malfunctioned. So that was exciting too. I think we actually have some data from that, but I'm sure the space agencies weren't thrilled with that outcome. And this is actually kind of interesting. This is Alex operating Falcon Neuro from the what they call the operations center for the thing. You know, I always feel like satellite stuff should be more dramatic and grand than it is. And everyone thinks of these sort of like ESA and NASA mission controls. It's really just a big screen with lots of buttons on it. And it's kind of funny because the guy who designed this interface, the part that talks to it, when you click a button, it says, do you want to do this? And you click yes. And then it says, do you really want to do this? And you click yes again, and it sends the command. So it's kind of cool. You actually have to talk to NASA and say, can we have permission to operate our instrument? So really interesting. And we learned a lot from how to actually operate these things. So I'll talk quickly about the results because they've been kind of spectacular. This, I went too far, sorry. This is actually the first, go back one more. Sorry, there's a delay between the two. So this is the first bit of data we got from Falcon Neuro. That's the raw data from the sensor. And we did a bit of, you know, it definitely looked like we're seeing things. And then a lot of work went into how do you actually take the data and figure out where you are and what you're looking at. And after doing some processing, this is the nadir camera that looks down. We actually managed to essentially motion compensate for the ISS and take those events and put them into a stabilized image. And you get this long, thin image like this of data from the ISS. So essentially you're stacking up as a feature comes into field of view, it marches across the field of view, and you can take each of those columns, if you know the time, and align them, and you get this actually quite high contrast image of the ground. That white box there is the field of view of Falcon Neuro, of the camera. And as you move, you can then create this long image as the world sort of passes underneath you. And you can actually...
Is that in kilometers?
It's a good question. Each pixel here is about 300 kilometers. So this is quite a large portion. This is, I actually don't know off the top of my head. Do you have a sense, Alex?
Yeah, so each pixel is
300 meters.
So the width covers something like 100 meters. No, wait, no, it's not that. Sorry.
Yeah.
Multiply that by
But, yeah.
And is the stuff in the blue picture that's going on the screen like clouds that you're thinking of?
No, some of it's probably clouds. So if you look here, it might be hard to see on the projector. So you'll see that a lot of the structures, like this little bit of land here, lines up really nicely with the ground. This doesn't. This is probably clouds. And some of the work we're trying to do is use parallax to separate the clouds from the ground because they're different altitudes. But we definitely see a lot of clouds, but we also see a lot of ground features as well. And sometimes telling them apart is actually part of the issue. But this was a huge result, saying A, it worked, and B, that we could actually figure out where we were looking, because non-trivial task. I wish you could say it was automated. It was very much a manual align until we find, because we thought this was Panama, but it wasn't. It was actually over Honduras. So really exciting, really great data from this. We were really happy with it there. Turns out you can run these same cameras at night as well. And if you look at what the conventional camera looks at night, you don't see anything because it's just too dark. Also, I should say that this is the field of view of the current sensors that we have on the ISS. The next mission that's launching next year is closer to this. It's an HD sensor, Prophecy Gen 4. So we'll get that sort of size resolution. You can imagine what that's going to look like. When you run at night, however, you actually can get some pretty good results as well. Weirdly enough, we see streetlights quite often. So, and there's some really interesting things you can pull out from this. But having a sensor that can run both at night and during the day for observations, and I think this was the standard biases. We hadn't changed them yet. We can definitely tweak the biases to get better performance at night. That's a really, really important facet of this because that's something conventional sensors really, really struggle with. And if you go look at the live feed from the ISS at night, you'll see that usually. Yeah.
You see this long rectangle there? Could you call that a strip map, or is that a different thing?
Which is this long?
Yeah, the section of land that you're capturing.
A strip map.
Yeah, like in synthetic aperture radar.
Yes, it's very similar to that actually. Yeah.
I wanted to ask. So, is the section of land that you're capturing with your nadir-facing camera, is it the same section of land that other Earth observation instruments on the ISS capture, and can you combine?
Unfortunately, and if you go back to this one over here, yeah, you've hit the nail on the head on the sad truth. That is the HD camera on the ISS.
So you're capturing completely different chunks of.
Yeah, the fields of view do not overlap as much as we wanted them to. We thought they were, but they didn't. So we have nothing to correspond to actually correlate the data with. And
when you were designing the mission, was it your intent for them to have an overlap or not?
No, but for the next one, it is, and it was, and we got around that by putting context cameras on so that we can take our own images.
Oh, so you're adding
yes,
a traditional camera next to where you're. Okay.
Exactly, for that exact purpose, because that's the lesson we learned from this, which is don't assume that all the fields of view overlap, even if you're on the same part of the ISS. So that was an interesting lesson that we learned. Just to go into a little bit more detail about what we do, this is an example of a recording, really noisy as you can see. We did a lot of work on the motion compensation side of things. How do you take this and turn it into those nice Earth features? I had a student who did quite a bit of work on this, and Alex, it was actually one of Alex's ideas about how to actually compensate this and produce these nice maps from that by figuring out essentially contrast maximization, but optimized for this type of observation. And there was a nice paper that he actually wrote with it's an analytical technique to make that a slightly more efficient process. And in fact, if you run it over things like the Suez Canal, right, well, you can actually create these nice maps where you can actually find ships and then align them with the actual shipping data. And the reason we can do that is that, you know, we have the resolution we have per pixel means we can only really see really, really large ships. And that's about the only place in the world where you get lots of really large ships. And the data really matches up nicely. In fact, he even went and found pictures of all the ships. So Sammy really did a great job of being thorough with this. And it's actually kind of an amazing result from that, given that field of view. This is another really interesting nadir recording. This is a massive lightning storm as we're passing overhead. So this was actually the primary mission. This is lightning observed over China as the ISS is moving. To give you a sense of what we're actually looking at, I could say Falcon Neuro, I apologize. It's 180 seconds of data, 12 megabytes in size. Yeah. Just the sensor's noisy. And also partly it's the way we're rendering it, but the sensor is really noisy. And that's a question we have for what's going to happen with the Gen 4 sensors. So, you know, we can take this lightning here and we can do that same technique of sort of making a nice stable image of it. And this is a particularly good example of it because you can see here, we actually have this long strip. So all of that data I showed you, all the lines up here. And then as you pass over, you know, you can see we have this beautiful long strip, this 180 seconds worth of data as we go right over the sea as well. So, you know, you can produce these really interesting results like this as we move. And, you know, the sort of lightning storms really proved that we can actually do lightning detection with this. In fact, as you saw, we didn't just see that lightning happen. We actually saw something about the structure as that lightning lit up the clouds. And potentially we could see more if we had more resolution. This is probably the most important recording. And this is the message that I really want to leave you guys with. This is a RAM camera recording. So this is the camera that looks at the horizon. We recorded this in February. It's 30 seconds long. It's 1 megabyte of data, and it doesn't look like much. There's a bit of structure here maybe, but we honestly almost threw this recording away and said it was noise. And I think this is a really, really important lesson for neuromorphic engineering, because I think a lot of people fall into this trap. They go get a camera, they go record something, they make frames out of the data like this, and they go, it doesn't work. Useless, and they chuck it away. Often it does work, and the data is in there, but frames are a terrible way to look at it. Take those lightning results I showed yesterday. You know, if you have that long recording and you render frames, the entire lightning strike happens in one frame, right? Unless you render it at an incredibly high temporal resolution. But you're looking for a needle in a haystack if you have an hour-long recording. You want to find the right 2 milliseconds to render at 1,000,000 frames a second. There's no way to do it. So you really have to find better ways to look at the data. So when we looked at this data, we almost threw it away, but we started playing around with it. And it's actually a great story because we were sitting down with some of our colleagues in our institute, because our institute is actually the Marx Institute for Brain Behavior and Development. So we're the neuromorphic side, and there's a whole bunch of brain sciences people and a whole bunch of psychophysicists. And they looked at this data and they said, this is easy. This is psychophysics. Just play it back faster and move it back and forth, and all the motion will jump out at you. It's the dots. It's a famous neuroscience experiment with these sort of dots where you can, just dots, but you can actually see structure, people walking in them. So we thought, okay, fine, we'll try it. And you know what? It worked like a charm. It worked fantastically. If you do that with this data, this is what you get. There's lots of structure in there, right? And it hurts me a little bit and makes me kind of proud that interdisciplinary science actually works as well as they want to sometimes, but it was a great result. And here you can see there's lots of structure in there. This is 30 seconds of recording. You might notice that we can clean it up a bit by changing the gamma RAM function. And you'll see here, this is really interesting. So now you can start seeing the geometry of the scene, the horizon somewhere in the middle. These are ground features moving backwards and forwards to the bottom here. There are stars going vertically upwards, which is really cool. But you might notice the object moving from right to left to the top there. That's a satellite. That's a satellite viewed from the ISS. That is the whole on-orbit detection of satellites that we're talking about, proved with actual real data. Turns out if you play with this a little bit more, you actually can find out that there's a lot more stars than you might think. There's tons there. There's enough to do an astrometric fit and figure out exactly where you're looking. Right, so now I've put the horizon in there for you as well. And if you notice, there's one object at the top there, but down to the right, there's another object as well. You might see a second one. Turns out there are 5 satellites in there, maybe even 6. And we went to figure out where those are as well, right? That's 1 megabyte of data, 30 seconds long. Now, a megabyte of data is something you can get down from orbit pretty easily, even with the slow connections we have, right? But ultimately, this really proves that when I talk about doing SSA from orbit, this is real. And the fact that we can see all those stars as well means that we can use it like a star tracker too. So we can use it to say, okay, cool, you're pointing in the right direction. So we solved that pointing problem. And that goes back to the sort of control tool ideas we're talking about now, yesterday as well in our topic. And you can do that whilst looking for other satellites. So, yeah.
Do you have any paper on that?
No, not yet. We need to write a paper. We have a lot of data and a lot of things going on. And I wish we had more time to write papers. So, you know, again, like this cool stuff here that we've done a lot more work than we may have published. So if you guys find something interesting, we might be able to give you half a paper to start it off. So please come work with us on this stuff. Yeah.
Do you have any idea the impact of having to read out all of that noise on like the accuracy at which you're able to capture this?
It's a good question. So there is a lot of noise in there, but keep in mind that with the noise, it's only a megabyte of data. And because we have motion and we know something about the motion, it really helps us reject the noise. So a lot of what we do is we don't tend to denoise anything anymore. We tend to try work with the data and some prior about the motion to extract the data out of the noise and just leave the noise in there. Because, and this is an open problem. If there's motion you've seen that you don't know about, how do you know what is signal and what is noise? And that's a really difficult problem. So noise filtering can be dangerous if you don't know something about your scene. Noise filtering works really well with a static scene, but not really as well if there's some motion. So there's some context around event-based data that's needed to understand and know what sort of processing is applicable. And then finally, this brings it all together. This is kind of the solved image. Here, we've actually identified the ground features here, which cities we're looking at. We figured out where we were looking in the sky. And Alex actually managed to figure out exactly which satellites we're looking at. And this is the distance from the ISS to those satellites. So really just an amazing result for this instrument. So we're really excited about this. And, you know, that's why everything we're talking about today, it's not pipe dreams. This is real. This is stuff we are keen to do and follow up on. So that's kind of the motivation for what we're doing. I'll quickly, before we break, I've got about 5 minutes left. I'll talk very quickly about Falcon Odin, the follow-on mission to the ISS. That's going to launch at the beginning of next year. This is a picture of what it looks like. It was called Falcon Odin because it was going to have one camera, and Odin is a one-eyed god in Norse mythology. Like everything else, it started with one camera. Now it has 4, so Falcon Odin doesn't really make sense as a name. But you actually see here the 2 context cameras. This actually has a whole bunch of mirrors in it, so we can actually move the field of view around. And it has fantastically upgraded optics as well. To just give you some sense of the scale of the thing, Falcon Neuro was about this size. Here, Alex is holding a scale model of it. That's the real thing over there. And compare the structure of this thing to a conventional laptop. It's about 30 kilograms. It's huge. And it's, you know, solid aluminum, so it's heavy as well. But that's the scale. It's like we really ramped this thing up, and it's going to be an incredible instrument when it's in orbit because it just improves on everything we've done so far. So it's going to use 2 Gen 4 sensors, one for nadir and RAM, just like the previous one. You might notice it has this interesting like triangular shape here. That was so we could peer over the ASIM instrument that has now moved into our field of view. So hopefully we'll have overlapping fields of view because they're literally in our way. And essentially we're going to take the resolution in the nadir camera from about 100 meters per pixel, or 30 meters per pixel, I think, down to about 12 meters per pixel. So that's really interesting. So we're going to have amazing ground resolution. So hopefully we'll be able to see the structure of lightning, not just lightning itself. And the RAM camera is going to be able to look up and down and side to side as well. So we can point it all the way up and look at stars. We can point it right down, look at the horizon for lightning. You know, really an interesting system to control and operate. We've designed a whole bunch of hardware for this to do it. Sorry. A dosimeter measures radiation. So it's just a sensor that just essentially gives you the amount of radiation that thing is absorbed over its lifetime. And it's just, we put in all our instruments, but the people we work with at the Academy have put on every instrument. So they have radiation data going back 10 years. You know, they've been putting things on the ISS for ages now. So just a really cool little piece of equipment. Bad news for you, everyone. This thing is a Jetson board, so I apologize in advance. But it was really, you know, we're not actually using the GPUs at all. So we're really using it as an industrial computer with USB ports. We were originally going to use MIPI to talk to the cameras, but the cable length for MIPI is a problem because we needed to have the cameras, you know, the instrument grew and grew and grew and grew until it was too big for MIPI to work, but still something we could support with this. So we built our own interface to that. This is actually kind of a mature thing. Hopefully it'll have space heritage. Lots of things we learned in this process as well. My advice to you, if you make boards for space, whatever quantity you think you need, double it. And then probably double it again. But you'll blow up boards, you'll lose boards. People will say, I need 4 boards for some arbitrary purpose. I'm going to drop a brick on them and see what happens. Just make sure you build lots of them. And, you know, it's fully functional now. In fact, I think this week they're loading the next version of the software onto the integrated instrument. It has multiple cameras. This thing runs 4 cameras. It works within the power consumption budget we have, which is about 20 watts maximum. And we've written a whole bunch of software in Rust, including drivers, which are publicly available for the Gen 4 cameras, which are actually really good. They're going to have space heritage, so they have to be good, we hope. So finally, just a little thing on like how we're going to operate it. So this is how we did Falcon Neuro. Everything was manual. We literally said, turn on our camera, and it turned it on. We're going to add a couple more. This is stuff we've learned from doing this thing. We really want to be able to schedule, say, I don't want to have to wake Richard from the Air Force Academy up at 3 in the morning to go look at something interesting. We want to just be able to say, turn on at 3 a.m., capture data and send it back to us. Then we want to do some onboard processing. We might not want to send all the data back. We really want to still select parts we're interested in. And then finally, what we really want to do is real-time processing. Say, did we see a lightning strike? And if so, take the last 30 seconds of data and send it back to Earth. So this is really stuff we've learned from going through this whole process of building the thing. Finally, again, satellites are messy. That is what satellite development looks like sometimes. It's terrifying. We actually built our own little flat sat here that we take with us in a Pelican case. It actually now has a monitor on there as well. Somehow out of this mess, an actual satellite has emerged. Now, I should say, we did use some AI in the whole Falcon Neuro project, mostly to name things. So this worked spectacularly well because we had this case with our satellites in it, and we thought, what should we call it? So we asked ChatGPT, or this is actually Bing Chat here, about you know, the story of Odin. It turns out Odin rode on an 8-legged horse called Sleipnir. So guess what our mobile little satellite development thing is called. So that's what, you know, everyone always asks me, is there any AI in your project? And I go, yes, there is. It's fantastic. Finally, this is probably my second last slide. If anyone knows anything about space, you'll discover that there's epoxy everywhere. Everything has to be epoxied and glued in. And that means that we're stuck in. And by the way, there's your Jetson board. And one of the reasons the Jetson was so useful is it has a metal case which you can then actually thermally attach to the housing of our instrument, which allows us to get heat dissipated away from us. Once something is glued in, you cannot get it out. So really, you have to test everything to the 9th before you have it installed. And that was a hard lesson because there are things on that board we would love to fix, but no one is willing to melt all that epoxy and get that thing out. That's a month-long work to get that thing out and back in. So, you know, you really have to get things right the first time. And so much design goes into this, so much review. And actually, the reason NASA does so many amazing things so well is because they've done it before, they know what they're doing, and they are painfully meticulous, but it works. So, you know, there's a reason why they go through all of this. This is a very, very expensive lens that sits in our telescope. That is our downward facing telescope, essentially. And we had to attach the Gen 4 camera and epoxy it in place. And so we had to figure out how to focus it in a clean environment, glue the camera in place and set the focus, which we did. We left it inclined. And epoxy doesn't set instantly, so it slipped a tiny bit. And the back focus on this lens is 12 microns. So you can imagine how much fun and excitement that was. But ultimately, you know, there's all these practical things that almost derailed the mission, but we're actually finding results from that. So I think that's everything I want to talk to you guys about. I'm going to leave you with some very pretty data from the ISS. And if there are any other questions, I mean, maybe we're basically on time now. So please come up afterwards. And yeah, I hope you enjoyed it and you come work with us. There's some stuff to do.